All right, so the foundations of structural equation modeling is on hand here. What I want to start off with is kind of 30,000-foot background, if you will, of where structural equation modeling, what the philosophical underpinnings behind it are. Because if you've had something like an ANOVA, you've learned the classical approach, that nil hypothesis testing, that we've been moving away from steadily. When I first got started in the late 1980s, structural equation modeling was a brand new school of thought and a brand new statistical way of thinking and approaching things. And the classical approach was absolutely dominant, like 99-1. It's still, the classical approach does still permeate a lot of our thinking about about statistical modeling. Fortunately, we're also seeing the influence of the Bayesian way of thinking about statistical modeling. And to be honest, the modeling approach that I'm going to be talking about is very much Bayesian, except for the estimator, meaning that we still use maximum likelihood. And then one of the reasons why we use maximum likelihood is that we have large sample sizes that would basically take any priors that you might put on a model and kind of wipes them out because of our sample sizes. But for the most part, we're going to be doing a lot of using prior knowledge, dialoguing with our data, and not kind of sticking to that. You can't, everything has to be a priori. It has to be, tested against a nil hypothesis type of way of thinking. We're going to look at the advantages of both approaches, because the experimental designs of the classical approach are still useful, but they definitely aren't going to be the dominant way of thinking about how to approach modeling data. So if we look at the two schools, it's the systematic design. The setting is the experimental world. The focus is on group differences. It's basically testing the possible relationships by controlling everything else. Is it possible that this variable could have an influence? It's generally well understood and easy to use, but it's really focusing on the trees in the forest and not the forest of the trees. Whereas the representative design, that modeling school that is thinking about the typical environment, the focus is on both within and between person differences, not on group differences. So we're looking at within person changes and between person relationships. And we're trying to test out the probable relationships among typically a very large multivariate situation. Right? So it is complicated, time consuming, and can be costly. But the benefits, I think, are you are generating models of the relationships among numerous variables to disentangle what is important relative to the other variables, what's not important relative to the other variables. And we're doing that all in a latent space where everything is on an even playing field that allows you to state mostly unequivocally what's happening. Now, there's still going to be, errors in our model, which we'll talk about here, that we need to be mindful of. But for the most part, we get a broader, richer picture of the relationships among the variables that we think are important to understand. Again, both are going to be important, but the modeling school gives us the ability to test quite sophisticated models. We can control for numerous confounds, and to the most part, we can implicate causality to a degree. And I like to use the lowercase version of it, because in my way of thinking, it's the verisimilitude or the truth-like value of the model that gives it the ability to inform policy and practice. And one of the hallmarks of structural equation modeling is the ability to compare and test competing hypotheses. So oftentimes we can get them to be nested model comparisons, so that we can say with statistical power, one model is better than the other model. Now, the classical school was very empirically driven. It revolved around the use of exploratory factor analysis, and they were called factors, and factors were derived from variables. It was very data driven. And then we have the null hypothesis versus the modeling school, which is a little bit more pragmatic. It's working on the idea of confirmatory analyses. And again, this is where the prior knowledge informs what the model should look like. And we call our factors are called constructs from the modeling perspective because we're constructing them using indicators, not variables, not necessary items. So we have indicators of constructs. It's very theory driven, and we're testing model hypotheses rather than null hypotheses. Again, the classical school, the advantages, it's easy to specify, well understood, doesn't require large sample sizes. Generally, if you get to around 40 individuals, you've got pretty reasonable inferences that you can make from the classical perspective, as well as there are many user-friendly software packages with canned procedures, but that can also be one of the problems of the classical school too, is you've got those graphical user interfaces with default settings that have really kind of dumbed down our ability to think about what we need to do and how we need to do it. So when Brandon was talking about things like Amos, it's like, yeah, that's one of those software packages that we don't want you to use because it's dumbed it down so much that you can't even, there are certain recommendations that we make that you can't even do in Amos because Amos won't allow you to go in and make those kinds of changes. It decided for you what it wanted to do and how it was going to do it, rather than allowing you to think through, well, here's what's going to be best for this research question. I want to do it this way. Classical school does not correct for measurement error, and it is one of the assumptions of the classical school is you've measured things without error. So all of your p-values and tests of significance are based on that assumption. And when that is not true, and it's not true for almost all statistical situations, you're going to have errors of inference. There are a lot of limiting assumptions in the classical school, like equal variances, no indirect effects. And again, the mindless use of it with the graphical user interfaces and the default settings will be problematic. When you not correcting for measurement error, we get inconsistent and biased parameter estimates. So variances are going to be too high, correlations are going to be too low, partial and semi-partial relationships are all going to be biased, typically on the low side. R-squared values are always going to be too low, and the regression parameters are going to be biased and typically on the low side. And that's because that measurement error is involved in it. You've got reliable variance as well as error variance in the variances. That affects the correlations, that affects the R-squared, and that affects the regression parameters. Right? You get lower power. There will be chance relationships that are capitalized on because that error variance is actually part of what you're analyzing. And therefore you will get reduced generalizability and inaccurate substantive conclusions. Now, with structural equation modeling, we'll start off with its disadvantages. It's complex. That's a definite truism. It's less well understood, although people are beginning, and I appreciate the fact that you all are attending this seminar because you are trying to get to that point where you are understanding it better. So not only to be a good consumer, but also to be somebody who can become a power user of the techniques. Sample sizes generally need to be on the larger side. It's based on asymptotic distribution theory. When we get to the discussion of sample size, you'll learn that the magic number that I like is about 120, unless I'm looking at, trying to make a super refined distinction between a semi-partial relationship between two variables that are extremely highly correlated. then I might want to have a larger sample size. But for the most part, 120 will get you a good sense of what's going on. The software isn't very user-friendly because it's mostly a scripting language that you need to learn outside of Amos. And when you learn the scripting language, well, that involves writing syntax, checking your syntax, finding the errors in your syntax, double checking your syntax, refinding more errors in your syntax. There are a couple software packages that we support and recommend. I was one of the original Lisrel users. I still prefer Lisrel, but it's not one that's very popular. We support M+, which has become pretty popular, and then Levon, and I'll talk about some others here in a few minutes as well. Now, the focus here is on model fit rather than local fit or individual fit. I will recommend some ways to examine local misfit. We like to focus on modification indices. And then there's also the finite mixture models, which allow you to determine whether there might be individuals where there's differences involved, the subgroups that might be present in your data, because one of the things about SEM is we assume that we're sampling from a homogeneous population of individuals that just vary in magnitude and not necessarily in type. One can know just enough to be dangerous with SEM. You see that oftentimes with reviewers who know a little bit about structural equation modeling and say that there are rules by which you must use SEM, when in fact there are very few rules. In fact, the only rule that I have for SEM is there are no rules. It's still going to be a matter of choice and justification on your part as the investigator. Advantages, we correct for measurement error. So every construct now is, as I said earlier, every construct is now put on an even playing field. A construct that has more measurement error than another one is usually at a deficit, because that measurement error hides so much of the relationship that that construct might have with other constructs if we analyze it using simple regression, for example. But if we put it into a latent variable structural equation modeling perspective, we separate out what's reliable from what's not reliable so that everything is on the same reliable playing field. The indicators that we use to represent that latent construct, we can examine those loadings, and those establish the content validity of the indicators. The multiple constructs that we use, we then have the construct validity being well informed. And we're also testing models of the expected relationships, plural, because we're dealing with typically a very massively multivariate world. And because of all of the steps involved, from what you're going to measure, how you are going to set up your model, the drawing that we use, it encourages very careful theoretical considerations. And when we are at the latent level, we get much more accurate estimates of the true unbiased population parameters, right? So we've dealt with sampling error, we've dealt with other things that will give us much greater generalizability. And there's basically any system of linear equations, whether they're direct effects, indirect effects, and we can also include nonlinear relationships now. Those have been built into the estimators for structural equation modeling. Again, testing direct effects, indirect effects, mediators, moderators, and any combination thereof. The other thing that's kind of cool about SEM is that we can establish the construct comparability in cross-cultural work. It's a concept called factorial invariance, which we'll discuss in here. It's applicable to any multiple group comparison or any longitudinal relationship that you're interested in examining. So modeling is a process, right? We have concepts, And those concepts are generally derived from things like intuitions, our reading of the literature, our discussions with colleagues, observations that we've made along the way. But then we're going to take those concepts and we're going to convert them into constructs. And from those constructs, we need to derive indicators of those constructs. So basically, we're going from theoretical definitions to operational definitions when we go from constructs to indicators. The concepts are dictionary definitions, right? So those are things that we all can discuss with somebody who's not part of our scientific world. But when we move into the scientific world, that's when we have to generate theoretical definitions to formalize more what that concept should be. So the construct is defining a space of where does that construct sit in construct space. It's as much about what it is as about what it is not. And that's when we get to the operational definitions where we define the indicators that say, okay, this is what can be used to represent this construct because it's within this part of the construct space. And then from that theoretical model, we go to a statistical model. Another key important understanding, I think, with modeling is carving up the world into meaningful units. Now, the puzzle pieces should follow from the same template. And I see a lot of times where people will go and they'll review literature and they'll pull a construct that comes from a more mechanistic viewpoint of human behavior, and then grab a construct that's more from an organismic viewpoint of human behavior, and put those two constructs in the same model, where you're using two different templates to carve up the world. And when we carve up the world, we have to carve it up into meaningful units. So if you're thinking about, a hand, the wrist, the elbow, shoulder, they all have to be carved up in those at those locations in order to piece it back together again to say, here, I've got an arm, right? Face, right? So if you carve it up improperly, you might get a one-eyed rendering of what should be a two-eyed face with a nose. So sometimes we have to consider where we get the constructs from and what the meta-theoretical perspective is that came up with those constructs. And using the same meta theory, whether you're using the Ravensburger or Springbok template, that's, choose one or the other, and then make all the constructs follow from that meta-theoretical perspective. Now, models too are basically organizing devices for a continuing explicit dialogue between assumptions and the data. Now, the other thing to keep in mind is that models are necessarily simplifications and only approximate reality. There's a lot of parsimony represented in our models. And the idea is to get to a level of parsimony that is, it's a huge cost-benefit analysis. Do I have a sufficient level of parsimony that allows me to maximize my verisimilitude and limit the costs of both data collection and modeling and representing the complexity of things that go beyond what is necessary to understand the phenomenon of interest? Now, please do feel free to chime in. I recommend just unmuting and saying, hey, Todd. If you send something to the chat, Zach will help keep an eye on it, but just unmute and jump in if you have any questions or comments. So in a nutshell, the I do seek acronym that I put together here, it starts again with that intuitions that are the concepts that we then formalize with designing a study, theoretical definitions, we operationalize with indicators, and then we bring in the data that we've collected and we specify what that model is, right? So we have a drawing and we take that drawing and we tell the SEM software what that drawing looks like. We hit the running icon to estimate the parameter estimates, we evaluate the model. So we're looking at model fit information, we're looking at modification indices, we're looking at the significance of the parameter estimates, the relative standard errors, and then we have to commensurate with non-significant relationships that are, we're looking at a lot of partial relationships that have never been examined before, so it's hard to know in advance which ones are going to be significant and which ones aren't. And so we're evaluating that. We're also looking at the modification indices to see if there are parameter estimates that are being suggested by the data, and then we have to consider whether the data's suggestions are reasonable. And then after that initial commensuration, we have a respecification, a re-estimation, a re-evaluation, and a further commensuration until we have satisfied that we have a model that represents the data sufficiently well and that we've achieved the greatest degree of verisimilitude for that particular model. And ideally, we've got model comparison. So we have competing models that we can test, but each of those models would have to go through an I-do-seek process until we can get each of the theoretical definitions or the theoretical representations fitting the data as well as possible, and then put them in a position where we can reasonably compare one model against the other. Now, models are used to depict behavior and experience, so we're trying to describe behavior transparently and systematically. We're trying to explain the forces that give rise to the behaviors. We also want to have prediction, right? We want to predict when and under what conditions behaviors occur. And all of this is to improve the quality of life by use of this knowledge. We are trying to inform policy and practice. And in a lot of sense, it's trying to control behaviors, changing the unwanted, solidifying the wanted, again, making those improvements to the quality of life. And the other key aspect of models is testing all of the above. Models are just renderings that are on the leaderboard. No model is true, no model is correct. It is just the best one available today, whereas the model tomorrow might have an improvement. We start using that model because we've tested it against the previous models and found that the newer model actually is better. Lastly, good models allow knowledge to leap forward. They need to be logical and internally consistent. There's a lot of circular reasoning that we see still in the literature and still in how people represent their structural equation models. We need to eliminate those, so we need that logic in there. They need to be empirically testable. Is the idea of falsifiability in philosophy of science. So things have to be rejected. We have to be able to show that something can be wrong, that it's non-significant, that it doesn't have an impact, that something is better. We still have to account for what we do know in the field. But again, typically models are not necessarily replications, but they're going to be semi-replications with extensions. So we're bringing in other constructs, or we're changing the context in which we're modeling, using a different sample, different things go on. So, but what we do know about certain constructs, we should be able to account for them given the literature. So if we have things that go contrary to the literature, we need to account for that as well. Given the model scope, what was the change? What constructs did we bring in that changed things? What was the sample like that changed things? And finally, parsimony is still one of our key goals in representing things with the fewer axioms or auxiliary hypotheses. The model with the fewest caveats generally is the better model than the one that has to explain weird findings, weird outcomes. So those where the auxiliary hypotheses come in. It's like, oh, well, that was weird. I'm going to have to come up with a reason for that. And you come up with an auxiliary hypothesis to explain away a phenomenon that you found in your model. If we can avoid that, that's better. So I do seek to depict human behavior to allow knowledge to leap forward. Right, there's going to be a lot of Greek involved in SEM. The blue here are the most common in both exploratory factor analysis and structural equation modeling. The cheat sheet that I created for my book that's on the inside cover. Here I use the distinction between the uppercase and the lowercase version of the different Greek letters. So an uppercase lambda, I also typically will make it bold. That's the matrix of loadings of the indicators on the constructs, whereas a lowercase lambda with, and I usually italicize it, and then it will have, typically it will have subscripted numbers, which I don't depict here, but there would be like a 1,1. That basically depicts which cell in the matrix is this parameter estimate coming from. And so we have psi uppercase, psi lowercase, which is the variances and covariances of the constructs. We have phi, which is the variances of the constructs on the exogenous side. We'll have theta, which are the residual variances of the indicators. We have beta, which are the regression estimates between constructs. Tau are going to be the intercepts of the indicators. Alpha is going to be the latent means of the constructs. We have also gamma, kappa, and that I'm not going to talk about much in here because I put everything on the Y side. So eta is an endogenous construct. Chi is the exogenous constructs, but again, I put everything, or I like to talk about everything as being endogenous because the assumption of exogeneity, I mean, we have to assume that I've captured everything from the very beginning, which if I'm not going back to the Big Bang, I can't make that claim of exogeneity. So everything is endogenous. I just picked it up at a certain point in time and carried it forward. Now, sigma is going to be an important part of this because sigma is the model implied variance covariance matrix that our model generates, and we're going to compare that to the observed covariance matrix. And then the other Greek symbol that's important down here is delta. That designates change, so change in chi-square or change in CFI, for example. Basic types of models, we have the confirmatory factor analysis model up here. We have a a path analysis here. So we have multiple regression, but it's among boxes. So we're not correcting for measurement error. And then over here, I have a structural equation model, again, a multiple regression, but it's among the latent variables. So I've corrected for measurement error because I have these multiple indicators down here to represent what's reliable up here in the latent construct so that these regression parameters are on an even basis. Later in our seminar, we'll have I'll show you where I get different regression estimates at the path analysis level than I get at the regression at the latent level, where one model shows that this is the stronger predictor, but in the latent space, it's this model, this construct.
Dr. Little, this is Kendra. I have a question.
Yeah.
So, you know, with my colleagues are doing different type of research, and I'm get confused when they call it SEM, but it's actually a path analysis. So what?
Yeah.
Am I asking the right question?
Yeah. So the big distinction between what I call a path analysis is when you're just doing manifest indicators. And I will call it a structural equation model when it's latent variables, because a structural equation model is a simultaneously set of equations that are being solved. You're solving the equations to define what the latent factor is and latent construct is, and then you're also solving for the regression among these latent constructs. Whereas over here, you're just solving for two parameter estimates that can be solved with the least squares solution. Here, we have to rely on maximum likelihood, and that's when we move into the world of structural equation modeling.
It makes a difference. So many times I think they're doing path analysis. That makes sense. Thank you.
Yeah. Now, you can do if you use an SEM software package to do your path analyses, the one advantage there is you can estimate indirect effects, but you're still estimating them among manifest indicators that are not correcting for measurement error. So there's kind of a gray area between a traditional regression model like I have represented here that can be solved using least squares versus, let's say I had a box over here and it was predicting this box, which in turn predicts this box. That can't be done in least squares analyses, but you could do that with with an SEM software package. But if it's the manifest variable that you're modeling, you're still in what we call the world of path analysis. Whereas if I have circles to represent latent constructs, that's when I'm in the world of structural equation modeling, because I'm simultaneously solving for what the construct is, and then I'm solving for the relationships among the constructs. And I can have indirect effects. So I could have a construct over here that predicts this construct, which in turn predicts this construct. Different SEM programs that are available. We talked about M+. It's probably the Cadillac of SEM software. Lisserl is a close second. It does quite a bit of the same things that M+ can do. Then you have R-based SEM packages. We will be emphasizing the Levon package. There's EQS, which was one of the original SEM software packages that Peter Bentler developed. I'm not sure whether that's continuing to be developed. I know that Peter retired a while back, and he turned that over to somebody else. Lisserl is being developed by SSI Central, so they were taken over. M+ is still being developed by the Mutanes, but they also are a company, and then they have other scientists working on it. So I expect to see M+, Lisserl continuing to be developed even after the originators have retired and or passed away. The other package that I don't have represented here is Stata. Has a very good SEM module in it as well. So if you're in the Stata world, you can learn that particular software package. One of our goals here soon is to work with the folks at Stata to develop scripts using Stata for all of the examples that we are presenting here. Right now, we have all the examples in M+, Lisserl, and Levon. All right, so the key point here was comparing the traditional versus the modeling approaches, recognizing the advantages and disadvantages of SEM, and basically getting into thinking about modeling from a modeling perspective. So any thoughts or questions?
I have a quick question. This is Jenny. So you don't recommend Amos because it doesn't, you said, capture like the nuances and those like more complicated relationships? Okay.
Yeah, there's certain things that we're going to learn in here, like using effects coding for identification scaling. Amos doesn't do that. You can't go in there and program it to do it, whereas the other software packages you can. And there are other disadvantages that Amos, just because it's driven by the graphical user interface, it sets defaults that you can't override that you may want to override. And so once you kind of get into that limiting space of using Amos, then you have to rely on, you can't change anything. Whereas all the other software packages are fully capable of allowing you to make any of the nuanced changes that we are describing in here, like using phantom rescaling constructs, effects coding scaling methods, etc.
Okay, thank you.
Sorry. I have a lot of like background data that would inform small data sets, and I'm wondering if SEM would be appropriate for that kind of a situation. If we have lots of little data sets that we're trying to piece together to get the understanding of what might happen with current small data sets. And like,
Yeah.
I know it's really designed for large data sets, and I do play around with some large data sets when it comes to like transcriptomics and things and microbial data. But if I'm primarily looking at a group of like 6 astronauts or pseudo astronauts, and I've got several replicates of this, is this going to be useful, or do I need to find a different tool to look at that kind of data?
It can be useful. There's a couple things there that can happen. It also depends on how you measure. So if you have intensive measurements of those 6 astronauts, you would have the ability to model each astronaut as its own model. And so if you got, say, 6 astronauts and you had intensive daily measurements of, affect with regard to their interactions with the plants on an hourly basis for the duration of a flight, right? That would give you thousands of observations per astronaut, right? And so what you can do is your SEM model would be a model for astronaut A based on the thousands of observations that he or she gave you. And you would have a 6-group comparison so that you can compare each of the astronauts against each other to look at their idiographic responses to interacting with plants. And that's actually goes all the way back to Ray Cattell's P-technique factor analysis, where you basically have the person is your focal group, and the observations are intensively measured for that person.
Perfect, thank you.
And Kendra, I think you had a question.
I'm good. Thank you.
All right.
Yeah.
Okay, now I think, Zach, are you going to take the next?
Yes, sir.
All right. Pause my video.
All right. I'll go ahead and share mine. And then we'll start talking about psychometrics. So I'm going over a lot of the psychometric qualities that we look for when we go through SEM modeling. We want to understand the process of measurement and defining constructs in the process of SEM, difference between reliability and validity, and sources of measurement error in our models, and understanding the interrelations among the validity triumvirate in SEM. And I'll cover what that is. And just like Todd, if you have any questions, just interrupt me and I'll be happy to clarify. Right, so when we talk about SEM modeling, we're usually measuring latent variables, but we're measuring those with manifest indicators. So when we look at our models, our latent variables are depicted as circles or ovals typically, and they are the construct of interest. They're what we're actually interested in measuring. They're typically invisible, mostly inferred from our measurement variables. And if we could measure them directly, we would, but since they're latent, we can't. And the way this is depicted is a causal relationship. So in this example, my latent state of aggression causes my answer on item 1, I hit others. So there is a causal regression relationship among our latent construct and the item that we use to measure it. So our manifest indicators are what we actually measure in our data set. It is what is on our columns in our data field. They are depicted as boxes or rectangles in diagrams like this. They are observable and can be measured, so they are measured. But they act as a proxy for that latent construct. And these can be a single item here, like item 1, I hit others, or item composites like parcels. We'll get into parceling a little later on. That's basically averaging 2 or more items together, but it's still a manifest variable on your data set. So what are constructs? They are the building blocks of a theory. They are the concepts and dimensions used to characterize behavior. They're also a theoretical abstraction. It is a hypothetical framework for us to build our theory. It's also derived from our theories. It's those knots in the theory's nomological net. And constructs are typically built by theorists and then used to explain phenomena they observe. And in our case, constructs are latent. They're presumed to exist within an individual, but they cannot be measured directly. But they can be inferred from overt behavior. And it is this overt behavior that we measure. So it's a quote from John Nesselrode: indicators are a worldly window into the latent space. They give us a way to access what is internal, what is abstract, what is unobservable. So now for indicators. We have several types of indicators. Most common is continuous. And even indicators that are measured on a 1 to 5 scale, we assume that 1 to 5 scale is representing a continuum. And we can treat it as continuous. And there's dichotomous, which is like 2 true categories. Classically, gender has been seen this way. We have male versus female, but also dummy codes act this way. You either have observed something or you've not observed something. You've either passed or not passed something. You either are part of a group or you're not part of a group, 1s and 0s. And then we have dichotomized, where we've taken a continuous distribution and then we've divided it into 2 arbitrary categories, like a median split or a low versus high IQ, where we've measured that initially in a continuous way, then have chosen a point, typically arbitrarily, to have made a dichotomous variable out of it. We also have polytomous variables, which are truly ordinal with more than 2 categories, where you have like education, high school, diploma, bachelor's, master's, PhD. These are truly separate categories. And just like dichotomous and dichotomized, we have polytomous and polytomized, where we have an underlying continuous field and we've arbitrarily divided it into more than 2 ordered categories, like low, medium, high income. And one piece of advice that we often give is to work on the continuous version of those variables rather than dichotomizing or polytomizing, if you can help it. So if you have truly dichotomous or polytomous variables, those are great to work with. But if you have dichotomized or polytomized, I would try and work with the continuous underlying variable that was used to make them. So here is another way of looking at indicators, and this table will be useful a little later on. We're talking about moderation and parceling. It's just a way of looking at the relationship between the indicators and our latent construct. So we'll look at parts of our measurement model that are intercepts, loadings, and residuals. If for all of our indicators of a construct, these are equal, we have parallel indicators. They're essentially equivalent indicators. Now, if the loadings and intercepts are equivalent, but our residuals vary, we have tau equivalent indicators. If our loadings are equal and our residuals, but our intercepts vary, they're called essentially parallel. If just our loading is equal, then they're essentially tau equivalent. If we have equal intercepts, but loadings and residuals vary, they're congeneric. And we'll find this a lot in our items. And then if everything varies, they're essentially congeneric. One difference between that classical regression theory and SEM modeling is your measurements are assumed tau equivalent or parallel in your classical version. And in SEM, we can actually allow for congenerity in our items. And we can test whether our items are performing parallel, tau equivalent, or if they're truly congeneric.
Zach, this is
Yeah.
Kendra. Can you tell me why this is important?
For understanding the benefits of SEM,
Mhm.
knowing that your items don't have to be tau equivalent, they don't have to be interchangeable, because when you have a scale score, when you're averaging items together, you're assuming all of them are parallel or tau equivalent. You're assuming they're contributing equally to a construct.
Okay,
But in SEM, they are allowed to vary in their contribution. So
okay,
one item may contribute a lot of variance to defining a construct, while another item doesn't contribute very much. And we can
Okay.
allow those to be different.
okay.
Does that make sense?
Yep, thank you.
And later on, when we're talking about moderation and constructing a moderator.
Yeah.
If you have tau equivalent indicators, it simplifies things. So,
And it's important to know this once you look at how the indicators are related to the construct. It's important to know what type they are.
yes.
Great.
There are also different types of relationships among constructs or indicators. So here are the different kinds of correlations that you can have among continuous, dichotomous, or polytomous indicators. So we have a lot of names for variables that are used interchangeably, but when you drill down to it, there's basically three types of indicators we're going to talk about: covariates, predictors, and outcomes. And these are examples of a lot of words that we use when we represent covariates, predictors, and outcomes. So control variables, nuisance variables for covariates, independent, exogenous, predictor variables, and then dependent variables, endogenous, outcome variables. So there's a lot of, each field tends to develop its own vocabulary. And we're just trying to kind of,
Zach, another question. These are
Yes.
types of variables for latent variables.
not just latent variables, these
I
are
know.
also used a lot in just
Okay,
regression analysis or path analysis. You have predictors and outcomes,
right, okay.
covariates. And here is a table kind of showing the relationship among indicators and constructs when it comes to either a categorical indicator or a continuous indicator, and a categorical latent construct and a continuous latent construct. So if you have categorical indicators and you're measuring a categorical latent variable, that is a latent transition analysis. If you have categorical indicators, but continuous latent construct, that's latent trait analysis or IRT. If you have continuous indicators, but a categorical latent construct, that's your latent class, your mixture modeling. And finally, what we're covering in this class, if we have continuous indicators and continuous latent constructs, that's your latent variable analysis, or CFA. But all of these can be modeled as different takes on SEM modeling. So here's a quote from Thorndike: "Whatever exists at all exists in some amount. And to know it thoroughly involves knowing its quantity as well as its quality." So when we look at measuring something, we need to start with operationalization, which is defining what we're trying to measure in a way that we can measure it. So we're defining a concept with specific observable characteristics. So in this example, hitting and kicking is the operational definition of overt aggression. We can observe hitting and kicking and use that to represent overt aggression. It's the process of linking constructs to their manifest indicators. What can we observe that represents what we're trying to measure? And we have our rule-bound assignment of numbers to the indicators of that which exists. Like we have a four-point Likert scale. But also know that you can make your own rules here. A lot of scales were developed with 4-point Likert scale or 5-point Likert scale indicators, but you can change that scale to 7-point scale. You can use a continuous slider. It's not a set in stone thing. So if you need to adjust a scale to measure what you're trying to measure, we give you license to do so. We also need to deal with measurement error. And this comes in several varieties. So we have truly random error, which are chance fluctuations, interference, noise. It's uncontrollable and unknowable, and it influences reliability. And we have non-random error, which is systematic influence, but it is biased. It's controllable and knowable if you're lucky, and it influences validity. So one example of non-random error is you have a social support scale that's given, and several of those questions ask about family. So those questions ask about a loved one. So the part of that question that's about family and the part of that question that's about loved ones, it's not about social support. So it's non-random error. You're measuring something you're not trying to measure. But it is going to always be a part of that question. So it's systematic. But it's measuring something that is separate from social support. So it impacts your validity. And we have the performance potential divide, which exists when people aren't indicating their true level of what you're trying to measure. So this can be influenced by motivation, attitude, social desirability. They don't feel comfortable reporting either how high or low they truly are on a thing. So I have the potential, but I perform below my potential. So here is an example of domain sampling. So we have a construct that exists at the center of this blue space. And there is an infinite number of potential indicators we can choose to measure this construct. And any random selection of indicators will point towards our construct. And some may be really good indicators of what we're trying to measure, like these three here. But the further we get from the center, the more measurement error we have. This is why we suggest having more than one measure or more than one indicator of a construct, so that by combining them, we can kind of triangulate around the thing we're trying to measure. So here's an example of our measurement error. This is highly centered around our bullseye. So these are reliable. This is a reliable measure, and it's hitting the center of what we're trying to measure, so it's a valid measure. But over here, we have a set of measures that are reliable. They're close together, but they're not valid. They are off-center. They're measuring something different. So we're going to talk about the different sources of variance that we need to consider when we're looking at our model. This is based on classical test theory. So we have our individual scores is based on the true score, what we're trying to measure. Specific variance, which is item-specific reliable sources of variance. This is that family or significant other portion of the question I was mentioning earlier. So every time I ask that question, it will be in my data. And then we have random error and noise that is truly part of what the individual brings or what the measurement occasion brings. Now we assume that the specific variance and the error variance are normally distributed with a mean of 0 and are uncorrelated with each other. Across all item domains, the S's are uncorrelated with each other, and so are the E's.
Zach, could you again just repeat specific item error? Because I know that's important.
Yeah. So specific item variance is a reliable source of variance associated with that item, but it's not part of what you're trying to measure.
Okay.
So going back to that social support scale, I'm trying to measure social support, but the part of that item that asks about friends or family or significant others, every time I ask that question, that part of the question is presented. So variance associated with family, significant others, or friends will be included in that variance. So it'll be common every time I ask the question, but it's not part of what I'm trying to measure.
Okay. Do you usually, in a sense, try to include that in your data so you can remove it?
Well,
That old thinking.
Yeah. Well, we need to know it exists, because if we have two questions that ask about family, they'll have a correlation among those sources of specific variance that's separate from the correlation among the perceived social support. So it's basically an additional source of variance or covariance that we're not trying to measure. So if we're looking at our model output and we have, say, 6 questions on social support, and 2 of those questions have family, we'll have some misfit if we don't either let those 2 questions have a residual correlation because there's something specific they share.
Great. That makes sense. Thank you.
Yeah. And we'll also talk about this source of variance when we get into parceling, because if you know you have questions that are asking questions that have the same sources of specific variance, you can parcel those together. And that just becomes part of the residual variance.
Okay. Thanks.
So then I'm talking about reliability, which is the degree to which the measurement can be reproduced. The more random the influences are on a measure, the less reliable it is. And for example, we have the Groundhog's Day movie, where if you can give a test repeatedly, would you get the same scores? And these is affected by random, non-systematic fluctuations that come from measurement administration, instrument or format fluctuations. If you give a test with a computer versus pen and paper, coding and scoring mistakes, guessing, fatigue, and motivational influences can add to your subject error variance. And then you have session fluctuations or paradigm error variance. But here in the bottom line, unreliability is a bad thing. But it is something that we can control for in SEM. Now, validity is the degree to which we are measuring what we are trying to measure. Are our questions getting at that construct? This is the theoretical accuracy of our measurement. It reflects how an indicator is used. And an indicator can be valid for some purposes, but not for others. So in this example, IQ score is an indicator of ability versus an indicator of the resource holding potential. So when it comes to an indicator, it can be valid for some purpose, not for others. Each time we run our model in a new sample, we are reestablishing reliability and validity for our indicators, just to make sure that those indicators function as they're expected to in our sample, regardless of how they performed in previous examples. So here is the validity triumvirate. We have construct, criterion, and content validity. Content validity is the idea that the items of a test or measure are homogeneous sample of the population or universe of possible items that can stand as indicants of a construct. Going back to that image of, I'll just go back to the image, that the items we have chosen do represent what we're trying to measure. And a quote from Kronbach and Meal: content validity is ordinarily to be established deductively by defining a universe of items and sampling systematically within this universe to establish a test. So a triangulation of indicators in SEM is a strong empirical test of content validity, and simultaneously it corrects for unreliability. So when we have 3 indicators of a construct, if all of those indicators are significant predictors of that construct, then that establishes our content validity of those indicators. They're all measuring the same thing. If we have an item that is not significantly loading on a construct and shows a strong cross-loading on another construct, then that shows that that item does not have content validity for what we thought it did, and maybe has content validity for another construct. But how well do the indicators of a construct converge on a construct and discriminate from others? Again, not having those significant cross-loadings and having significant loadings on what we're trying to measure. And we'll look more at these triangulations of validity when we get to parceling as well. And the strength of the relationship from indicators to construct, the loading, is the amount of shared variance among those indicators. Now for criterion validity, this is a relationship between the focal construct and an independent criterion construct. For concurrent validity, when the criterion is measured at the same point in time as the focal construct. And predictive validity is when the criterion is measured at some point after the focal construct. And another quote from Cronbach and Meal. In some situations, the criterion is no more valid than the test. So a good way to establish this criterion validity is to include multiple constructs in an analysis so we can see how they relate to each other. And if that relationship is what we expected. So how well does this pattern of associations among multiple constructs conform to our expected pattern? So I have PA and stress. Is this correlation among constructs what we expected to see? Is that reflected in our theory? Is it too high? Or is it too low? And by using multiple constructs, we can kind of see how our construct interacts in a field of related measures. And if this is all at a single time point, we have concurrent validity. And if we have it in a longitudinal context, we have predictive validity. And then we have construct validity, which is the ongoing process of amassing as much evidence as possible that supports the theory. And measure is an accurate representation of the construct. So the more times a measure is used, the different sorts of samples it's used in, the different sorts of environments that question is assessed in, this builds construct validity. And a construct is a vertical and distinct dimension of behavior. So beforehand, we may want to have a theoretical idea of how our construct relates to other constructs. And then when we fit our model, we see the empirical relationship among constructs that are estimated. And then our study extends prior work by using new samples, ages, cultures, and pits the focal construct against different sets of competing constructs. So every time a measure is used in a different context, in a different sample, this builds the validity of using those items to measure that construct. And this all is accumulating evidence that is constantly evaluated in terms of how it clarifies or supports the theoretical utility of that construct. So we answer the question, how well do these constructs produce similar results to past research using the same or similar constructs? It supports a measure is an accurate representation of that construct, and that this construct is a distinct dimension of behavior. And again, this is an ongoing process. We examine a construct in new contexts and in new samples. And we reevaluate previous studies, we reevaluate new contexts and see, does this measure and construct continue to perform as we expect it to? So, as a recap, content validity is established by how well the indicators of a construct converge on what it's trying to measure and discriminate from other constructs. We don't have any cross-loadings. Criterion validity is established by how well our pattern of associations among constructs conform to what we expect to see. And then construct validity is established by how well the construct produces similar results to past research using the same or similar constructs. It's the replication. And this evidence is constantly evaluated and reevaluated in terms of how it clarifies or supports the theoretical utility of a measure we're using. Any questions about the psychometrics? Let's see it.
Zach, this is Kendra. Thanks. No matter how many times we hear this, it's always a refresher.
Oh,
So
yeah.
to clarify, because they all start blending,
Mhm.
right? Thank you.
You're welcome. Well, if there are no questions, Todd, do you want to do a break or do you want to go on to the next?
I think a break would be a good thing right now. So we
Okay.
can take a 15-minute break, and then Dean, we'll take questions and we'll get started again.
Sounds good. See you at the 40.
Okay, so defining a construct. For some reason, the status bar that tells me I'm screen sharing and the chat and all that good stuff is in a weird location. If I can move it. There we go. So when I was learning structural equation modeling, the concept that just opened everything up for me was the idea of partitioning variance. So when you have a variable that you've measured and you get lots of responses on it, you will have a mean and a standard deviation, a normal distribution of scores typically. But that whole distribution is an amalgamation of different sources of variability. So that the variance in that distribution is a combination of true differences between individuals. It's going to be parts of a particular variable that are reliable, but are not part of the latent construct that you're interested in measuring. And then there's also going to be that random measurement error that Zach mentioned. And our goal in structural equation modeling is to partition those different sources of variance, divide them out so that we can isolate the true score variance that we're interested in. And that becomes our latent construct, whereas the amalgamation of all the variance is the manifest variable. So we can't do anything with the manifest variable except partition it into what's reliable and related to the construct, and then what is not. So we're going to get an idea of the figural conventions that we use, understand the sources of variance, and how we can partition them. Let's start with the figural conventions. So we use circles to represent the latent construct. Boxes or rectangles are the manifest measured variables. Right, so that's the actual observed scores that were input into your Excel spreadsheet, captured maybe by Qualtrics or made observations that were hand entered into some other database. Those are the columns of scores. Now the idea here is that we want multiple boxes that are similar in content that measure the latent variables. So we want to get multiple indicators of our latent variables. The other configural conventions, we use straight lines with a single arrowhead to represent a regression relationship. So it's a directional predictive relationship. And then we used curved lines with double arrowheads to represent the non-directional. So these will be either variances or covariance estimates. And then the last configural convention is the use of a triangle. Now, the triangle isn't a variable, it's the unit constant that we use to estimate the mean of a variable or the intercept of a variable when it's involved in a regression equation. If there's no regression, it's the mean. If there is a regression, it's an intercept. And an intercept is the mean of a variable when the variable predicting it is at 0.
Dr. Little, just a restatement. You said that that for the latent, we want multiple boxes that indicate the latent construct. That's what you said. Never
Yes.
mind. That makes
Yep.
sense. Now that I said it out loud. Thank you.
Yep, that's it. And ideally, we have 3 boxes to represent a latent construct.
Great. Thanks.
Now, these could be items that you've measured in a questionnaire protocol. Zach used the social support example. So we've got multiple items that measure social support. All of those items are boxes. And if we used an item level analysis at the full scale, I believe there was 12 total items. There would be 12 boxes and there would be 1 circle. The circle would be the social support information, and the boxes would be the items that you created that tap into the concept or construct of social support. So here is a sample diagram of 2 constructs. So we have the circle, which is construct A on the left-hand side and construct B on the right-hand side. We have the curved line. So when the curved line with double arrowheads starts and stops at the same circle or same box, that is going to be a variance parameter estimate. So the lines are the parameter estimates that we actually estimate. The circles and the boxes are the variables that we use to get the covariance. The construct predicts the indicator. Okay? So the arrows go from the construct to the indicator to predict or to capture the amount of construct variance in this indicator. And that goes back up through this regression and gets averaged here as the variance that these 3 indicators share that represent this construct. And then over here, we have another set of 3 indicators that have 3 regression parameters. The information is drawn up into an average variance estimate. What's left over is the residual variance of the indicator. So this is going to be the stuff that is specific to that indicator that is not the construct, as well as the unreliability or the random error. So it's the sum of those 2 components. And then we have the covariation between construct A and construct B. So if this is social support, how much does that influence your well-being, right? So the covariance between well-being and social support would be represented up here. This would be the variance of social support that was common among the 3 indicators of social support that you used. This would be the variance that's common among the 3 indicators of well-being that you used to capture the construct of well-being. Now there's kind of 2 ways to represent that residual information. So again, we have a parameter estimate here that is labeled theta 11. So that is the estimated residual variance. A traditional drawing would have the common factor, which is often called eta. In this case, it would be eta 1, the first construct. We have the 3 loadings, which are represented in a matrix called lambda. So lambda 11 is the first indicator's loading on the first construct. Lambda 21 is the second indicator's loading on the first construct. Lambda 31 is the third indicator's loading on the first construct. But then we have the residual of the first indicator, and that's often called a unique factor. So we could represent that as a circle. It's a unique factor. It's a latent construct. It's what's unique to Y1 that is not related to the common factor of eta. But there's only one parameter estimate being made here. So this regression relationship is a fixed 1.0. So the only thing being estimated is the residual variance of theta 1,1. So a preferred shorthand way of representing that is to simply have the curved line attached directly to the box and not put in the unique factor with its fixed 1.0, because we still have the parameter estimate theta 1,1 represented in our model as the residual against the y, and then theta 2,2 and theta 3,3. And so this is it's 3,3 because it's the third box coming back to the third box. And here it's 2,2 because it's the second box coming back to the second box. These are both mathematically identical. I prefer the right-hand way of doing the representation. It saves ink, space, time, all kinds of things. Now, Zach mentioned this before, but we have the score of a variable, of a measured variable. We can think about the person level as well as the between individual level. But so if we think about it at the person level, my score is a combination of my true value of what you're trying to measure, plus my particular reaction to that particular item. So if it was the social support item, but it was asking about friends, I would have a true score of how much social support is being measured by that item. But I would also have the reaction to the fact that it's friends that you're asking about and not family. And so there's going to be something specific to that item based on the fact that it was using friends to tap into my social support. And so we disentangle the true score of social support from the stuff that is specific to the item or the way in which you got at my social support, plus the truly random error that occurs in responding in that particular item. Now, in classical statistics, we assume that the T of each item is tau equivalent. Now, Zach showed that types of indicator slide where we had parallel items, tau equivalent items, essentially tau equivalent items. Classical test theory, manifest variable test theory, assumes at least tau equivalence. In SEM, we can actually allow for congeneric indicators. Some indicators can be better than others. So again, a construct is what the indicators share. So here we have X1, which has a true score, something specific to X1 and the random error of X1. And then we have X2, which has a true score. And so when we estimate the construct, the T's out of each of these boxes goes up into the latent construct. The loading is the amount that each indicator contributes to the construct. And in SEM, these can be what we said was congeneric. So this could be a 0.3, a 0.5, and a 0.7. Right? So 0.7 would tell you that 50% of the variability in item 3 is true. A 0.4 would tell you that 16% is true. And a 0.3 would be that only 9% is true. What's left over is the unexplained variance. So if everything's standardized, these would add up to 1.0. If not, the loading plus the residual would be the total variance. And so the residuals can be also different in magnitude, but they should be uncorrelated with each other. Now, this is an assumption of the classical test theory. It's also an assumption that we make in SEM, but we can evaluate that assumption by looking at the modification indices to see if there's any evidence of a correlated residual. And excuse me, depending on the degrees of freedom or how many indicators we have, we might be able to correlate those residuals to take the bias that occurs when residuals are in fact correlated and take it out of the model so it doesn't conflate our latent construct information, because this is what we want to identify, isolate, and partition. We want to partition the common variance from the unique variance, which is the sum of the specific and error. Any questions? Here again is that slide, the indicator typology. Right, tau equivalence means that the intercepts and loadings are equal. And we can have congeneric though when it's when the intercepts are equal but the loadings vary, and we can have essentially congeneric when the intercepts and loadings and residuals all vary. And this lowest level of measurement is actually acceptable within the SEM framework. Whereas in classical test theory, we need to be at the tau equivalent level in order to meet the assumptions of classical test theory and manifest variable regression analysis, for example. Right now, we can also bring in ideas of generalizability theory here. So we have C, which is the construct variance that we're interested in. And now I'm using I as an indicator for indicator N. There's going to be method variance, and there's going to be occasion of measurement variability. So something that is more transient, it's related to the time of measurement. So that there are three sources of variance that are part of the true score. Right? The method variance is unwanted. In longitudinal research, the occasion of measurement is typically what we're focusing on, and C becomes the stability information over time. We also have something that is unique to that particular indicator. And we have the essential unreliability. Okay. And each of these elements are independent of each other. So when we're doing our modeling, we're attempting to partition each of these sources of variance into certain locations. Now, typically with S and E, we isolate that as the residual variance and the sum of S and E. So we don't necessarily decompose S from E, but we want to get rid of this, the information that's in parentheses here, as part of the residual of this particular indicator. And then as part of our structural equation model, we're going to focus on these elements to start doing some prediction of what's stable, what changes. And if we have common method variance, we might be able to extract a method factor to eliminate M from the common variance that this indicator carries into our latent variable model. It's also possible that you have some occasion of measurement that is specific to that item, right? So you could think of it about being a bad hair day or whatever, but there's something about the occasion of measurement that makes the S larger at this occasion of measurement, and at the next occasion of measurement, S is lower. So the occasion of measurement can still influence anything that is reliable across time. And again, a construct is what the construct shares. So if we use the stable method occasion way of thinking about the true score, then when we estimate our latent construct, it's going to have the information that is stable across the indicators, the common method variance, and the common occasion of measurement information. And then the residual would be what's specific to this particular indicator, plus its error at this occasion of measurement. Now, indicators can vary in a couple of ways. One is in their operational definition, how vague or explicit the operational definition is, and then whether we're dealing with what we call multidimensionality. So multidimensionality would be a simple arithmetic problem where you have 2 digits over 2 digits and you have to add them up. Or you might have a math word problem, something like Arna has 6 bananas, Kirsten has 8 oranges. How many fruit do they have together? And so that involves disentangling the math information, doing the math problem. It involves verbal ability and so on. Vagueness would be when you're talking about substance use versus alcohol use items. Alcohol use items are very explicit, whereas substance use can be all kinds of different substances that you might use as part of your operational definition to examine substance use abuse versus alcohol use. The constructs also can vary in terms of their dimensionality. So a multidimensional construct would be something like intelligence versus a unidimensional aspect of intellective functioning, which is verbal facility. Right? Dirtiness would be something like numerical ability versus math that might include method variance. So you might be, everything would be measured using a paper and pencil form of a verification type task. That's going to get at math ability with method variance versus other ways of measuring math ability using a computer where it might be a production-based task or verification items. So you eliminate the method variance and you get them to be less dirty. Okay. So a dirty construct is not good. We want to try to minimize the degree to which we have method variance or other sources of variability that are represented in our construct that we don't want to measure. Multidimensionality is fine, but we just need to understand under what conditions we are dealing with multidimensionality and what we want to try to say about that degree of multidimensionality. So when we get into the parcels lecture, we'll show you how we can create parcels when we have multidimensional constructs that optimize how to represent that construct given the nature of the multidimensionality. So again, simple addition items as indicators of numerical facility. This is a very clean unidimensional construct. The construct is what the indicators share, and it's going to be a nice unidimensional representation of arithmetic ability. The math word problems is going to be a multidimensional construct because we're going to have the verbal ability plus the arithmetic ability, and actually you'll have other sources of sequential processing that are involved in a complex math word problem. But it's multidimensional and it contains both math and verbal variance. Now here we have complex addition items as indicators of numerical ability, but they're all done with a paper and pencil format of the method of how we're tapping into it. So in this case, we're going to have a construct that's going to contain common method variance. Oops, wrong direction. Common method variance, right? So then this construct would be dirty because of the shared paper and pencil format in which I measured complex arithmetic ability. So ideally, I would want to use indicators down here that have different methods for tapping into complex addition. So I might use a reaction time format, a paper and pencil verification format, and a paper and pencil production format, or another computer-based task, but one might be a verification format. What I mean there is the answers are given and you have to verify whether the answer is correct or incorrect. A production task is when the answer is not given and you have to actually produce the answer. Now here we have a situation where we have two items that share the same format. One is a different format. The tendency is for the stuff that is shared is going to want to be captured into the latent construct. So you end up getting poor model fit and you still get some contamination. So ideally, we would want to estimate the residual that is common down here so that it doesn't come up into the latent construct to contaminate it, and we get improved model fit. Now, with just 3 indicators of a construct, this is not identified. So what we'd end up needing to do is creating a 4th indicator from whatever we've measured so that we can capture this common method variance down here. We could also treat it as a common method construct, right? So this is actually what's called a bifactor model, where we estimate the method variance as a construct, and it's independent of the construct that we're trying to measure, that we're focusing on, but we still manage to extract the common method variance and eliminate it from contaminating our construct of interest. So we can clean it out by either correlating the residual or adding a common method factor for the construct. So when we look at the relationships between variables, so if we have maybe an example of simple arithmetic skill and complex arithmetic skill, they should be relatively highly correlated because they share arithmetic skill, what's common in red, then stuff that's related to the simple stuff, but each indicator has its own unique item-specific variance that goes into the overall aggregate, and then there's also the aggregate of unreliable variance. Over here, we have the different method variances, the common construct variance, and the average. And when we look at the correlation between these two manifest variables, the correlation might appear to be 0.5 because the common stuff, the 3 things that are shared, and this should have been actually the purple A's and the purple C's, that's what's overlapping. The stuff that's not overlapping is all of this other stuff, but you see it's got the measurement error components in there. So if we really want to know what the true relationship between simple arithmetic and complex arithmetic is, we need to estimate it as latent factors, because the latent factor of simple arithmetic will only contain the arithmetic components. We're going to leave behind the stuff that is specific to this item, as well as the unreliability of that particular item. Again, the sum of these 2 things becomes the residual. And now we see that 3 out of the 6 elements are overlapping, which gives us a correlation now of 0.7, right? So about 50% overlapping variance versus 25% overlapping variance once we control for the amount of measurement error. So all of this is the measurement error, and up here is the common variance, so that we can look at the true, what we refer to as the disattenuated correlation between these 2 constructs. Whereas in the previous slide, this correlation is attenuated, it's reduced, because measurement error is still a part of the denominator when we look at the overlap between complex arithmetic and simple arithmetic. Now, when we have shared method variance, so here I'm depicting constructs that have a shared component to them, that shared component adds to the overlap between the 2 constructs. So the shared method variance will elevate the true correlation between these 2 constructs. So what should have been a 0.7 correlation now appears to be 0.8 because we had a shared method component. If we have different methods, but the construct over here of simple arithmetic, each indicator shares at that common method. So let's say we did paper and pencil over here for simple addition, and over here we did reaction time for complex addition. The correlation will be reduced from what it should be, because now the not shared method variance is over here as part of the denominator when we look at the overlap between simple arithmetic and complex arithmetic, and the non-shared method variance is over here in the denominator when we look at the overlap between these two constructs, so that we have a reduced correlation, given that we have two different methods for measuring these two different constructs. Again, ideally, we want to get this method of information isolated as either part of the residual by using different methods down here, or estimate some kind of a construct, which is a method construct. So we have other constructs that have been measured using reaction time, and we could create a method construct of reaction time methods. And then over here, a paper and pencil version of another construct that we could estimate a method construct. If not, then you just need to know that your correlations are probably smaller than what they should be when you have non-shared method variance, and that the correlations are higher than what they should be when you have shared method variance. Now, relative differences will be intact in either case. So when you talk about relative differences in the strength of association across groups or across time, those are going to be valid comparisons. It's just we don't know whether the absolute magnitudes of those relationships truly should be if we have not addressed this issue of common method variance or non-shared common method variance. Any questions there? Okay, so in selecting indicators, one of the cool things about structural equation modeling is that reliability and validity are two distinct, separate sources of variance that we can evaluate in SEM. In classical methods, they are combined and there's no way to disentangle validity from reliability. In fact, it is commonly said that you cannot have validity without reliability from the classical psychometric perspective. But from a latent variable structural equation modeling, I want you to understand the circumstances when good indicators are bad and bad indicators are good. Here I'm making a pun or a play on the idea that we could have highly reliable indicators that are not valid, and we could have indicators that have very low reliability, but in fact are good, they're valid. And this comes from an article that John Nessel wrote, Uman Lindenberger and I wrote in 1999, where we did a simulation study to demonstrate quite clearly the circumstances when good indicators are bad and bad indicators are good. So here we have two indicators that are missing the construct centroid. So both of these are bad in terms of validity. In this case, the items are very far apart, which basically means the further the items are from each other, the lower the reliability, the lower their common variance. But the construct centroid that this triangle is pointing to is over here, and it's missing the centroid of what we want to measure. So this is a situation where we have items with low reliability and which are not valid. Up here we have a circumstance where we have items that are highly close to each other. So they would have strong correlations with each other, meaning they would show high reliability, but the construct centroid that they're pointing to is over here, again, missing the construct centroid that we're attempting to measure. So this would be where we have good indicators as represented by reliability, but bad as represented by the validity with which they are measuring the construct centroid that we're intending to measure. So our objective here is to target the construct centroid. So here's an item, another item. When we have two indicators, the construct that it points to is going to be the midpoint of the line that connects the two indicators. Add a third indicator into it. The construct centroid is going to be the geometric center of the three items. Add another item, and we're going to get the geometric midpoint of the four items. Add another indicator, and we're going to get the geometric centroid of the fifth item. And so as we get more and more items, we get better and better triangulation onto that construct centroid. Okay. Now, we can also think about the construct centroid in terms of selection spheres. Right. So here I'm looking at this. So here I'm looking at the top. I'm looking down onto a construct centroid. This circle is a selection plane, or is the construct, the sphere of construct that I'm after. And I have selection planes that are close to the construct centroid, selection planes that are further out, and so on. So when we look at, so here, for example, we might have items that have loadings of around 0.3. Selection plane here are items that have very little specific variance, but also low levels of communality. An item from this selection plane on the other hand has a great deal of information that is unique to that item, and only 0.3 of it is related to the construct centroid. As I move up with better items, so these have greater communality, now we're getting closer to the 0.5 region. And again, we have items that have very little diversity versus items that are way out here that have diversity. And then the distance from the selection plane to the outer circle, this amount is the amount of unreliable variance that items from this selection plane represent. And as we move further on up, we get highly reliable and load and working in on the construct centroid better and better. So again, when we talk,
This is Kendra. Can you
Yeah.
have two? Can you have too many? Are you trying to keep it parsimonious at some?
yeah, that's it. I mean, that's when we're doing measurement, we want to try to achieve a parsimonious number of indicators to represent the construct as accurately as possible, but we don't have to worry about reliability in SEM. So if I can get 6 good indicators that have modest reliability, then I have enough to represent that latent construct. In classical test theory, you would need to get more items to make sure that you had sufficient reliability.
Right.
And so in the classical world, we do lose a lot of that parsimonies, and we also start getting redundancy in the items. And then we start getting test reactivity because of the redundant items. And so there's a lot of negatives that go into, and then plus fatigue. So there's a lot of negatives going into asking participants over and over again about their social support, when we maybe only need 6 items to really tap into it at a modest level of reliability so that SEM could do the work.
And could you restate that it superficially sinks in, so we don't have to worry about reliability with a smaller number if in fact, can you finish that thought?
Yeah, as long as we can demonstrate the validity of the construct centroid that we're measuring with those 6 items, we have all the evidence that we need that those 6 items are accurate.
Great.
And here you're going to want to look at, we would move beyond content validity, which Zach talked about earlier, because the content validity is going to show that you have low loadings, but we can look at the criterion validity. So the construct that you're measuring that had the low loadings, that had questionable reliability, we can look at the correlation of that construct with all of the constructs that we've measured. And if all the correlations are in the expected direction and at the expected magnitude, then we have evidence that we have in fact hit this construct centroid. So here I have the perfect world where the items are really reliable and they're measuring the construct centroid. So here I have kind of a win-win situation. Over here, oops. Over here, I have the same level of internal consistency. The triangle is the same size, but the construct centroid that it's measuring is way over here. It's missing the point. So what I would see here in terms of content validity is the correlation of this construct with the construct over here would be too high, and the correlation of this construct with the construct down here would be too low. So I wouldn't have the construct validity that I would expect if I was measuring the construct here at its centroid. But because in SEM, I can still triangulate on a construct even with low levels of reliability. Here's the situation where I have items that are not highly related to each other, and they're measuring a construct centroid that's off. So in this case, the correlation of the construct would be too high with the one down here and too low with the one up here. But oops. Here, the fourth version is the same level of internal consistency as this poor construct, but it's focused, it's right on this construct centroid. So using my criterion validity correlations, it has the right magnitude of correlation with the construct over here, and it has the right correlation with the construct over here. Right? So examples of constructs that have low internal consistency, but could be highly valid are things like SES, attachment in the attachment world literature. They generally do not correlate very highly with each other, but in an SEM framework, we can demonstrate that they have a great deal of validity after we control for their low internal consistency. So when we use confirmatory SEM, so basically much of our validity information is going to be based on the confirmatory factor analysis model, or the CFA part. That's the measurement model for any structural equation model. Then when we move into the structural models, when we convert the estimated covariances among the constructs in the confirmatory factors analysis model, we convert them into directed regression relationships. That's when we move from CFA into SEM. Right? But confirmatory analysis are very good. There's no evidence of bias, and it doesn't overcorrect when there's measurement error. It does just the right amount of correction for reliability. You can have validity without reliability. You need good theory. You need good content validity evidence. And the other thing is think about it. So if you make better selections and think about it, you'll avoid what's called the allure of the bloated specific. Now, the bloated specific is, let's say I let's go back to, let's say I went to a situation like this where I had 6 items that were measuring the construct centroid, but I needed to create a short form. The tendency to create a short form is to look for the 3 items that correlate most highly with each other.
Right.
If that was the case, I would select this item, and this item. And what would be the construct centroid that these 3 would be pointing to? It would be over here. And that's because I chose the 3 items that shared specific item variance over here, instead of selecting this item and maybe this item, so that the triangle that these 3 items would be pointing to would still be the construct centroid that I wanted to. They would have lower reliability, but they would be pointing to the correct construct centroid. Whereas if I selected these 3 based on their internal consistency, I would get what Cattell referred to as a bloated specific. The construct has too much specific variance in it, and so it's no longer valid. It would have too strong of a correlation with constructs over here and too weak of a correlation with constructs over here. Stop my screen share unless somebody wants me to go back to a specific slide. Questions? One of the things that I forgot to mention this morning, Zach and I will be available for consultation during the lunch hour. So if you want to go grab your meal and bring it back to your computer and ask us questions about your data, your project, or any questions you might have about clarifications of part of the lectures. Our lunch hours are kind of working lunch hours. So I'll run and go heat up a plate and come back. And when I get back, Zach will go run and heat up a plate and he'll come back. And then we'll also have, I think, access to Abby, who is one of my students and has taken this class, and she'll be available to help answer any questions you might have as well. Kendra, you're on mute.
Thank you. The last part seemed to come together, but back in the beginning, when we were talking about relations among constructs, it got a little overwhelming, but suffice it to say at this point, is that like trying to discriminate your constructs? Is that what we're trying to do at that point? Trying to.
Yeah, we want to have a certain amount of construct discrimination.
Okay.
So we have convergent and discriminant validity issues that we would examine as part of our overall, what I call criterion validity coefficients. So again, some of these constructs you expect to be quite divergent, and when you measure and you estimate and you don't have that divergence, that's a threat to your validity. If you have the divergence that you're expecting between those two constructs, then you have support that you're measuring the constructs in their right location in construct space.
And that was not merely, but an illustration of the dirtiness and the multidimensionality, just how that's so complex.
Okay, so dirtiness generally will deflate your construct correlations.
Okay.
Multidimensionality will generally be an issue of, well, what dimension of your construct is responsible for the correlations that you're seeing? So there it's a matter of interpretation, whereas
Okay.
dirtiness is a matter of confounding. It will almost always, well, it depends. If you have two constructs that share the same dirtiness, it will inflate the correlation. And if they don't, and if you have two constructs that have different sources of dirtiness, it will reduce the correlations.
Thanks.
Zach, I don't remember if we put 12:30 as our lunch hour or 12 as our lunch hour. Remember?
Let me check.
Yeah.
I think it's 12.
Okay. I think we still have time to start lecture 4. And
Okay.
we'll just pause and try to find a spot to pause when we get close to 12. And then we'll take our lunch break. But again, we will be here if you want to ask questions about your data and your projects.
That works for me. I'll go ahead and start sharing on my end. Okay. So in this lecture, we'll start talking about model identification. This is the point where we move kind of towards applying our SEM, building our models and things that we have to do in order to actually fit and evaluate our model. So we're going to go through scale setting and identification. We'll create latent variables from 1, 2, 3, or 4 or more indicators. And we'll go through the 3 different methods of setting your scale for your latent variable model. So what we're trying to measure, our latent construct, is not defined in our data. It's not measured on our data set. So it's kind of an amalgamation of shared variance among our measured indicators. So it's kind of mathematically floating around. It doesn't have a point of reference. So what we need to do is fix a point of reference so that the rest of our parameters can be in relation to this point of reference. Todd describes it as finding a point and putting a doink in that cloud of shared variance. Now, this reference point is arbitrary, but it will impact how we interpret our parameters once our model is fit. But where we put this reference point doesn't impact our overall model fit. It's just kind of, we have to find a point and set it as a reference. And then from that point, everything else is relative. So here's an example of a just identified model with 3 indicators. We have our 3 indicators and we have our latent construct. So in order for us to find a solution to this problem, we need to set a reference point. And here in their latent variance, we've fixed that value to 1. And this allows for the rest of these parameters to be identified. It's sort of like if I have x plus y equals 5, what is x? I don't know, because x and y can take on infinite number of values. But if I say y equals 1, I now can solve for x. And that's kind of what we're doing when we fix that point of reference. So in this just identified model, I have 6 pieces of known information. I have 3 variances and 3 covariances. And so from these pieces of known information, I need to estimate my unknown pieces of information. So for a just identified model, that would be these 3 loadings and these 3 residuals. So I have 6 knowns and 6 unknowns. That will use up all my knowns, give me degrees of freedom. And I use those degrees of freedom to estimate parameters. And for every parameter I estimate, I use a degree of freedom. I can't use more degrees of freedom than I have. I can't calculate more unknowns than I have knowns. And a just identified model is where you have equal knowns and unknowns. So an over-identified model is when we have more knowns than unknowns. We get degrees of freedom back. And an under-identified model is where we have less knowns than unknowns. We have negative degrees of freedom, and this can't be identified. So you have an example, x plus z equals 5. We have an infinite number of solutions. We need to reduce the number of parameters we have to estimate. So in this instance, I have 1 known piece of information. I have the variance of x1. But I'm trying to estimate 3 pieces of information. So I'm under-identified. Now, setting that reference point by fixing the variance at 1 takes care of one of my under-identified parameters. This sets our scale, and this is known as the fixed vector method of identification, or we fix our latent variance to 1. So now I have 2 unknowns and 1 known. So I still have my problem. Well, what I can do is I can make a limiting assumption and fix my residual variance to 0. I can say that my x1 has no residual variance. It is all true score variance. That my x1 is measured without error. Now, this is probably not always the case, so that's why we call it a limiting assumption. It forces all of the variance to be on the loading. So I can recreate the variance of X using our tracing rules. If you don't remember those, the variance of X1 is loading times common variance times loading plus residual. So lambda squared times psi. This is our psi matrix. This is our lambda matrix. And our residuals are theta matrix. So lambda psi lambda, or lambda squared psi plus theta. And that gives us a loading of 0.8. So take the square root of that, or square that, sorry, you get 0.64. Now we can move this one around. Like I said, placing your point of reference is arbitrary. So instead of having my latent variance fixed to 1, I can fix this loading to 1. And this is called marker method. And this is actually the default method in every SEM piece of software that I'm familiar with. It will always fix the first loading to 1. And so this keeps our limiting assumption that this is perfectly measured, but now my variance of X1 will be recreated up here in psi11. And says that the variance of my indicator is the variance of my construct. So this 0.64 is now up here. Go back to my tracing rules. I have 1 times 0.64 times 1 plus 0 gives me back my measured variance. Now, there is an alternative you can do if you have a single indicator. It's another limiting assumption where you take a known reliability estimate for your parameter, and then you subtract that from 1. So we have the variance of the indicator times 1 minus its reliability. So if you have previous times that this measure is used and you have an estimate of its reliability, you can basically fix its unreliability down here. Again, it's limited because you're not using your sample's variance, you're using established literature's measure of unreliability. So we assume a reliability of 0.9. So 1 minus is 0.1 times the variance is 0.064, which gives us a construct variance of 0.576. And so if we do our tracing rules again, 1 times 0.576 times 1 plus 0.064 returns us to our initial variance. So this is a illustration of the different ways we can do the single indicator identification, where we use marker method and have assuming no measurement error and assuming estimated reliability. This puts all of the cheerful's variance on the latent construct. Or we can fix the latent variance to 1, have no measurement error or assumed unreliability, and then have estimated loadings. Both of example 1 and example 3 here will have the same, actually all 4 of these have the same model implied variance for cheerful. These 2 will have the exact same fit, and 2 and 4 will have the exact same fit. Where we put this 1 doesn't impact our fit, and we'll see that later as well. Any questions on single indicator? Okay. For two indicator constructs, we have the same problem, just not as bad. So we have three pieces of known information. We have two variances and a covariance. But we're trying to find 5 pieces of unknown information, 2 loadings, 2 residuals, and 1 latent variance. I can take care of one of those by fixing my factor to 1. This identifies my model. But I still have 4 unknowns to 3 knowns. Now, in this case, we make another type of limiting assumption that these 2 indicators are tau equivalent. They have the same loadings. So loading on X1 and loading on X2 will be the same, but the residuals will be different. So we're just estimating one parameter that satisfies both these loadings. And this model finds that 0.75 will recreate X1, 0.75 times 1 times 0.75 plus 0.08. And then 0.75 times 1 times 0.75 plus 0.25 gives us 0.81. Now to get this covariance, we do loading, so 0.75 times 1 times 0.75 down the other loading, and that gives us our 0.56. Now we can do this with either the marker method variable, where the loadings, the first loading is fixed to 1, but since these are made to be equal, both loadings will equal 1. And this represents the variance of both glad and happy. And they'll each have estimated unique variances done here. Or we can fix the latent variance to 1, and both loadings will now equal 0.629. We see that didn't impact our residual variance. Whether the one was here or the one was here, it accounted for the same amount of variance. Now, finally, we're at the 3 indicator just identified construct. So we have 6 pieces of knowns, 3 variances and 3 covariances, and 7 unknowns, loadings, residuals, and latent variance. We'll use the fixed factor method again for fixing that scale. So we can now estimate each of these parameters without having to make any limiting assumptions. This is why we advocate for at least 3 indicators, so you have a just identified model. So for the default method of identification is marker method. The first loading will be fixed to 1. But you can move this loading around, this constraint around to the different indicators, and it's really an arbitrary decision. So if glad loading is fixed to 1, the latent variance of positive affect is the reliable variance of glad. And then cheerful and happy are in relation to glad. If cheerful is our marker variable, then positive affect's variance is the reliable variance of cheerful. And then glad and happy are kind of in relation to cheerful. And same with happy. As you see, the variance down here in the residuals don't change. So we're explaining the same amount of variance. It's just our point of reference changes our interpretation. Is our latent variance a positive affect reflecting glad, cheerful, or happy? All of these models will fit the exact same. You'll have the exact same model fit. It's just the interpretation of these parameters shifts, which isn't very helpful, which is why we've used other methods of identification. We'll cover fixed factor and eventually effects coding, which basically sets the average loading to 1 and puts this latent variance as the average common variance or the average reliable variance of all 3 indicators. So it's in the metric of what we measured. So here we have 4 indicators, which means we have 10 pieces of known information, 4 variances, and 6 covariances. And we need to measure 9. So if we're looking at degrees of freedom, we have enough degrees of freedom to estimate everything. But now we're back to that initial part of our presentation where we don't have a reference point. So we still need to identify this factor. So we'll fix that latent variance to 1. And now with 10 pieces of observed information, we're estimating 8 unknown pieces of information. We now have degrees of freedom left over. We'll have 2 degrees of freedom. And we are over-identified. Now, being over-identified locally isn't necessarily good, because as this construct is associated with other constructs in our model, Todd describes it as a 4-legged stool that as you shift the weight, these loadings can move around on you. While if you have a 3-legged stool or just identified stool, it can't shift around. So the relationship among this construct and another construct stabilizes. So here we have our variance covariance matrix using tracing rules. We have lambda times psi times lambda plus theta on the variance. And then the covariance is lambda times psi times the other lambda without the theta. And so our 3 methods of setting our scale, we have fixed factor, where we fix that latent variance to 1, which is what we've been showing here. The marker method, which where we fix one of the loadings to 1, which is the default method in every piece of stats software that I've encountered. And then we have the effects coding method, which constrains loadings to average 1. We'll kind of go through the variance covariance matrix tracing rules for each of these. So with this variance fixed to 1, these psi's become 1. So now it's just loading squared plus theta, or loading times loading for the covariances. So covariance between x1 and x2, lambda 1 1 times lambda 2 1. x1's variance is lambda 1 1 times 1 times lambda 1 1, or just lambda squared, plus theta. For the marker method, this first loading is fixed to 1. Again, it's kind of an arbitrary decision. Since the software automatically fixed the first one, the variable that just happens to be the first loaded becomes your identifying variable. But this recreates the same variance covariance matrix. And now with effects coding, we have lambda 2.1 and lambda 3.1 estimated. And then we have lambda 1.1 equals 3 minus the other 2. This has these 3 loadings average 1. So it's kind of taking the marker method, fixing this one to 1, fixing this one to 1, fixing this one to 1, and finding an average of those 3 models. So now this psi can be freely estimated as the average reliable variance of all 3 indicators. This allows us to have a latent factor in the same metric as our measured indicators, which can be really handy for interpretation. So if these 3 indicators were measured on a Likert scale of 1 to 5, our latent variable will be on that same scale. For a fixed factor, fixing this to 1 standardizes our latent construct. So this one has a different benefit of producing a standardized latent space. So this construct has a mean of 0, standard deviation and variance of 1, the standard normal. And any relationship among these constructs is now in a correlation metric. So that correlation is more interpretable than a covariance. Effects coding, any relationship among these constructs is in a covariance matrix or covariance metric. But these latent constructs are on the same scale as what we measured, so they become easier to interpret. And we'll talk in a bit about a way of having our cake and eating it too, with phantom constructs, but we're not quite there yet. Before I move on, are there any questions about these 3 scale setting methods?
Just as a point of clarification, Zach mentioned that the marker variable is the default method. It's one that we don't recommend. If you are going to be in an arbitrary metric, use the fixed factor method. But the effects coded method of scaling is very useful, particularly when the construct's original metric is of meaning for readers. So if you're going to create a descriptive statistics table of the means, correlation or covariances, variances, etc., if you did effects coding, you can just report the information from that particular method. You don't have to go back to your raw data, which has measurement error. So this gives you the information of your constructs corrected for measurement error and in the metric that they were originally scaled.
So going back to my social support scale, if these are social support items, I can have average social support. I can have that social support latent constructs, mean and variance, in the scale that I measured it in. So it's more interpretable that way.
So we are closing in on the noon hour. Is that? I can't remember what the slide deck looks like for in terms of a good stopping point, but
Yeah, I think we should go through, we can come back after lunch and go through the math to kind of re-solidify.
Yeah.
Chasing rules. And also have some demonstrations in R to kind of show what these look like with data input and output.
All right,
Any
so,
questions before we break for lunch?
yeah, do you have any questions on anything?
This is Kendra. It seems like the one indicator is the most problematic, or
Yeah, you make the most assumptions with a
make
single
them, that's what
indicator.
I meant. Okay.
Yeah.
Okay.
You have to make the
And-
most limiting assumptions.
Which makes sense in general as well. So, but in some cases, that's all you have.
Yeah, that's like, sometimes when you're dealing with data sets that are public use, they might have just the scale average and they don't have the items anymore on the data set. And so all you have is that information you can use. And you would have to create a single indicator version of that scale.
And sometimes in management, we have like employee performance and we only have one indicator of it.
Right. Yep, and there's no way to get to.
No. And even if you get to, they don't really go well. Okay, thank you.
Sometimes we have to use this for like variables like age that are measured
True.
as one item or continuous, but we need to put it in the latent space.
Okay.
So
And just conceptually, we scale in order to make it usable. So,
Yeah.
okay, otherwise it can't be solved. It's an equation that can't be solved. So we have to scale it so that it has a reference point, going back to your first slide.
Yep.
Just to kind of pull it back together. So we're scaling it so that we anchor the cloud.
Right. And you
It's
could think of it like temperature.
Okay,
We happen to use Fahrenheit as our scaling for knowing that it's a 100-degree day is hot and it's going to be 20 degrees cooler tomorrow. We have a sense of what that relative difference is in Fahrenheit, but we can also do that in Celsius, right? Or Kelvin, right? And they all are different ways of trying to scale what is the temperature. They would, and when the temperature is the same outside, these three different scaling methods of scaling temperature will give you a different number, but they're now relative to each other. So you can interpret a difference in Celsius of 30 to 20. You would have a sense of what that means if that was the metric that you were used to working with.
okay, but it's
Yeah.
still the same.
It's still the
Temperature.
same temperature and the same change in temperature.
Yeah, that helps to go back to the cloud. Thank you. Now the cloud makes sense.
good metaphor.
So another quick question, follow up to that. So I've often seen that when individuals only have a single item that they'll include it as a manifest variable.
It depends on the software package.
In the model that they're doing.
So M+, for example, will allow you to have a manifest variable predict a latent construct, but other software packages don't. And
Okay,
so you have to move the box up to be in the same world as the other latent constructs that you're measuring.
gotcha.
And the other advantage is if you did have a reasonable estimate of the reliability of that single indicated item, that you can use the scaling method where you fix the error variance to be 1 minus the total variance times 1 minus the estimated reliability. And so you can get a disattenuated version of your single indicator. So if you were using a public use data set and you had a scale on there that you knew its general reliability from other studies that have been published in the literature, well, you have a good estimate of reliability that you could use to control and estimate that amount of unreliable variance.
Right, thank you.
And again, what's the risk or the risk of using manifest to predict latent or vice versa?
You can't correct for measurement error.
And some software packages won't allow you.
Yeah, and some software packages just won't allow it. Another advantage is if you fix the variance at 1.0 and then estimated the regression, you would be getting a standardized regression relationship between your circle version of your manifest variable. Whereas if you just had a manifest variable, the only thing you can get is the unstandardized. So this would allow you to rescale the manifest variable to be standardized and then get standardized regression coefficients when you're looking at the relationships of it with other constructs. So 2 advantages to moving that box up to the circle space. Any other questions? Zach, I think you can go ahead and pause the recording. This will be our lunch hour now. And
All right, so I'm going to pick back up with model identification, go through a few more examples showing how we can recreate the observed correlation
Zach,
metric.
before you get going, I want to make,
Yeah.
It's a subtle distinction and it's easy to kind of slip language-wise, but right now we're talking construct identification. We typically talk about model identification when we have 2 or more constructs involved. So the identification and scaling that we're talking about right now is just at the level of a given construct.
Right. So we'll go through these examples showing how we can recreate this observed correlation matrix with our different methods of scale setting. And then I'll go into R after this and kind of visually show you what each of these look like and how they don't affect model fit, but can change how we interpret parameters. So here we have our observed correlation matrix between great, cheerful, and happy, which is measuring positive affect. And I should also state that the goal of what we're trying to do is to make a model that, as close as we can, recreates our observed matrix. So when we talk in a couple lectures about model fit, fit evaluates how well our model recreates what's there in the data. So we'll find parameters here that recreate this observed correlation matrix. So here are implied equations using tracing rules. So like the variance of R11 or great is lambda 11 times psi 11 times lambda 11 plus theta 11.
Hey, Zach, I'm sorry,
Yeah.
this is Kendra again. Could you slowly go back over tracing rules? I know we went over quickly, but with the lambdas and psis, I get confused. Could you go over just visually?
Yes. So tracing rules allow us to recreate this variance covariance matrix with the parameters on our model.
Okay.
So to recreate the variance of great, we see our equation here is lambda 11 times psi 11 times lambda 11. And lambdas are loadings. Psis are latent variance. And thetas are our residual variances. So this would be lambda 11 times psi 11 times lambda 11. So we go up, around, and back down. That's the
Okay.
tracing of our variance. And then we add on this portion, because between this and this is 100% of the variance in grade.
Okay,
So we've basically disentangled, or we've partitioned the variance in grade into what's in common with the lambda psi lambda and what's unique in the theta.
thank you.
So with fixed factor identification, we fix this psi 1, to be 1. So now instead of having psi 1 here, it becomes a constant 1. So now we're just solving for lambda values and a theta value. We have 0.76 times 1 times 0.76 plus 0.42 equals the 1 that is 100% of the variance in grades. Now for the correlation between great and cheerful, R21, it's lambda 1, so 0.76 times 1 times 0.8. That recreates that 0.61 in the correlation here. So this makes a standard normal latent construct where all of these become 1. Now for marker method, by default, the first loading is always fixed to 1. So in our equations, we have 1 times psi 1 times 1 plus theta 1 is a variance of great. So you see how the variance of great, the reliable variance, becomes our psi 1 variance. And then all of our other relationships are in reference to the reliable variance of great. And are the values that recreate that correlation matrix. So you have 1 times 0.75 times 1 plus 0.42 to recreate that 100% variance. Now, we can move this one around if we wanted to select a different marker method or marker variable, because the selection of a variable is kind of arbitrary, but it just rescales our construct so that great and happy are in reference to cheerful, because this is the reliable variance of cheerful. And we can do it for happy, which changes our latent construct variance to 0.66. And now everything else is in relation to happy. So all 3 of these markers, as well as the fixed factor, will recreate this exact same correlation matrix. It just changes the numbers needed to arrive at that solution by moving that 1 around. Now, the final method is effects coding, where we estimate this loading as 3 minus the other 2. So these will each have parameter estimates, and then this will be 3 minus whatever these 2 were estimated to be, which will make these average 1. So instead of selecting 1 to be our marker, these loadings will average around 1. So this one's a little below 1, and then these 2 are a little above 1, but they'll average 1. And now our latent variance is the average reliable variance of all three indicators in the scale of our original indicators. So just another, I just want to reinforce again that the method of setting our scale does not affect model fit. And I'll demonstrate that in a second. But it does affect the parameter estimates and interpretation of our constructs. Do we have a standardized construct where all the relationships are in correlations? Or do we have an unstandardized construct where all the relationships are in covariances? Is that latent variance in the metric of all of our items or just the one we've chosen as a marker? So the two methods that we advise people use is effects coding, if that original scale is meaningful, if you want to be able to interpret your latent construct in the same scale as your measured indicators. Or fixed factor, if you want to obtain standardized unit-free estimates that reflect the indicator reliabilities. And then you have standardized relationships among the constructs. They can report as correlations.
Can you tell us why you don't like, or why number 3 is a marker variable?
We don't recommend marker because it's an arbitrary decision,
True.
which indicator becomes the marker.
Okay.
And then your latent construct is kind of defined by whichever indicator
Okay.
was chosen to be the marker.
Kind of messy interpretation.
Yeah.
Yeah.
So both of these allow for more interpretable understandings of what that latent construct is and the relationship among them.
Thank you.
Mhm. So we've gone through scale setting and identification, how to create latent variables from 1 to 4 or more indicators, and when you would need to apply those limiting assumptions for 1 or 2 indicator models, and why, when you get more than 3 indicators, your construct can shift around with those loadings, which is why we prefer a just identified 3 indicator model. And when we talk about parceling, we'll talk about how you can have more than 3 and then parcel down to 3. But now I want to show an R example of these 3 methods of scale setting. So this example is in the Zach's example folder of the Dropbox, and it is SEM examples with AAM data. That is agency, achievement, and motivation. So here's what that data set looks like. I have an ID variable, gender, age, what classroom they're in, and then 3 indicators each of agency, achievement, and motivation on a Likert 1 to 5 scale. Now we can look at the observed variance covariance matrix. So this is the variance covariance of my observed data. And what our model is going to try and do is recreate this the best it can with the structure that we give it. So in Levon, I have agency being measured by agency 1, 2, and 3, achievement 1, 2, and 3, motivation by motivation 1, 2, and 3. So I'm using the default method So we see that here my first loading on each construct is fit to 1. It's automatically done. Something in the variance space has to be set to 1. If you just let the computer choose where to put it, it'll put it on the first loading. This is default in Levon, default in M+, and I believe it's the default everywhere else. I've not found a place where it's not the default. We have our model fit, and we'll talk about model fit later, but spoiler alert, this is good model fit. My chi-squared statistic and degree of freedom, CFI and TLI, RMSEA, and SRMR. So my loadings, first ones are fit to 1. My relationship among constructs is unstandardized. So these are covariances. And the standardized version over here would be a correlation. I have item intercepts, which are basically the means of my measured variables. And then my latent mean. You'll find that just like in the latent space or in the variance space, something has to be fixed to 1. In the mean structure, something has to be fixed to 0 for identification. So typically either for marker variable method, the latent mean is fixed to 0 or the mean of the first indicator is fixed to 0. In Levon, by default, the latent mean is fixed to 0. And then these are my residual variances or thetas for each indicator. So these are lambdas, these are thetas, and then this is my variance or my latent constructs or my size. So variance for my first indicator of agency, my measured variance is 0.3808. And if I take the latent variance of agency here, plus the residual, which is the theta, this is my model implied variance for agency 1. It's very close. And this is the model implied variance covariance matrix. So this has variances and covariances for my indicators and my manifest means. I pull this up so we can see that as we go through the different methods of identification, this doesn't change. Model fit doesn't change, and my model implied variance covariance matrix doesn't change. The only thing that changes is the actual parameters up here. So for fixed factor, the only thing I have to do in Levon is add an argument. Standardized latent variable is true. This changes it so that instead of having a loading fixed to 1 and the latent mean fixed to 0, the latent variance is fixed to 1 and the latent mean is fixed to 0. So this standardizes my latent space. So the model fit is the exact same. Same chi-square, same degrees of freedom, same CFI and TLI, same RMSEA, same SRMR. But now I have estimated loadings for all of my items. Nothing here is fixed to 1. My 1 comes back down here to the variance. That is not fixed to 1. But because these are fixed to 1, my covariances are standardized. You see this column of estimate and the standardized column are the same. So this is now in a correlational metric. see, achievement correlates with agency at 0.566. So that is now in an interpretable metric. And then I have my manifest item intercepts here. My latent mean is again fixed to 0. And then I have my residual variances here, my thetas. This top matrix is my original marker method, and this is my fixed factor. They're the same, model implied variance covariance matrix. So the only thing that's changed are how we can interpret these parameters. But they result in the same end variance covariance matrix. Now, the third method, effects coding, takes a little bit more syntax in both Lavon and in Plus, because you have to add labels to each of your loadings. So L11, L21, L31 here. Your labels can be anything you want them to be, as long as they start with a letter. I use L for lambda, T for tau down here for intercepts. One thing you have to do for effects coding is put in these formulas that we showed here for estimating this loading as 3 minus the other 2. So you see I have 3. Lambda 11 is 3 minus lambda 21 minus lambda 31. Now we have to do something similar for the intercepts to make them average 0. So tau 11 equals 0 minus tau 21 minus tau 31. Since you have to put a 0 somewhere in the means structure, this makes our item means average 0, which pushes that mean information up into the latent space and gives us a latent mean. And I'll show you what I mean here in a second. So for this model, I have the same model fit, same degrees of freedom, same fit statistics. But now you see my loadings average 1. And my relationship among constructs is back in an unstandardized metric. So this is now back in covariance relationships. But I now have means for my latent constructs. I have an average latent agency score of 3.102. So now I have a weighted average for agency, my construct, not just the items. I have a mean of achievement, a mean of motivation in that 1 to 5 Likert scale that I was using to measure as items. And I have variances for my constructs, agency, achievement, motivation. This puts my latent constructs on a scale that's the same as my measured indicators, allowing me to interpret them as if I would just an average score from my scale. And they result in the same model implied variance covariance matrix.
Zach, I have a question. I know you've given us coding examples in our folder.
Mhm.
And I'm assuming these are in it.
Yes.
So are we able to look at these without the software? Like I haven't looked yet, but is it like a PDF that we can kind of bond with, or do we need to have
The
software?
R example, you would need R to look at, I believe. But there are M+ examples as well.
So if we don't have the software yet, though, let me just ask you outright, is it possible for you to print PDF so I could just kind of look at them and I make notes on to kind of get more bonded with the outputs if we don't have the software yet?
Yeah, I can put the output in a PDF and drop that in the folder.
That'd be awesome. Just for tonight to like solidify what you're talking about.
Yeah.
And write like little lambda on the side thetas and thank you.
Yeah, of course.
You want M+ and R?
Yes, please. Well, to me, M+ is best, but I mean, R, if anybody else is interested, then it can like look, it was really helpful to see how the different models have different, how it's coded kind of solidifies how the modeling has to work. But yet it turned out the same, so.
Yeah,
Because they don't
And-
have the same labels like lambda and thetas, just a leap of faith for me right now.
and so in Zach's examples in M+, we do have effects coding, fixed factor, and marker method,
Okay,
input and output. So,
I don't have M+ yet though, so,
well, the thing with M+ is you can open all of
Oh,
its
really?
files
okay.
in like Notepad. So you
Oh,
can
awesome.
look at the input and
Oh, that's good
output.
to know. Then I'm good. Then I can do it that way.
This has the input and output for this. It's the same example, agency achievement,
Awesome.
motivation.
That's what I'm gonna do right now. Thank you. Perfect. I can print that. That would meet my need.
Are there any other questions regarding model identification? Again, somewhere in the variant space, a 1 has to be put. And somewhere in the mean structure, a 0 has to be put. Software has defaults for where those go, and it's usually marker method, the first indicator. But where you decide to put that 1 doesn't change your model fit. It just changes how you interpret the rest of the parameters, because kind of like that cloud example where you put that point of reference, everything else has to point to that point of reference. And this example and the data set are provided for you in my Zach's examples folder. This script has more to it than just identification, because we'll talk about parceling and invariance testing. So there's a lot of stuff on here. But this at first bit is model identification.
So I guess I'll kind of revisit a lot of this in the next slide deck. Number 5 is on confirmatory factor analysis. Get my screen share here. Oops, wait a second. Share real quick. I'm going to turn on my video. So now share screen. Right, so we're going to start off.
We're looking at your browser.
What's that?
We're not seeing the PowerPoint. We're seeing your web browser.
Okay, sorry.
Hey, Zach, did you put great, cheerful, happy as subliminal messages to us?
That wasn't my decision. That was Todd's.
I think it's working. I might not know what's going on, but I'm happy and cheerful.
Glad to hear it.
Glad to hear it, yeah. All right, can you see my screen or my slide deck?
Yes.
Okay, thank you. So I'm going to start off with an exploratory factor analysis and how we can then recast that as a confirmatory factor analysis. I'm sure many of you are familiar with an EFA, but a confirmatory factor analysis is also called the measurement model. It's what you're going to build your SEM on. That's why the last bullet point here says every SEM model begins with the CFA. So we'll look at nested model comparisons and model modifications. We're also going to look and see the matrix algebra that is that underlies the tracing rules that Zach has referred to. So here we have the great, cheerful, happy, and then we also have the negative affect. Here, if we looked at the raw Pearson correlations among the items, and this would be something to get in the habit of doing, is organize your correlation matrix by the indicators that you think should go together to form a construct. And what you should see is something like this: a strong positive manifold of correlations among the three items that you think go together to create an underlying latent construct. And similarly down here for the negative affect, we've got a strong manifold of high positive correlations. The other thing you should look at is see similarities in the correlations in this part of the matrix here, where these are the three positive affect items and how they relate to the first negative affect. And within sampling here, they're all right around that 0.1-ish mark. And then here for negative affect 2, it's a little bit higher. And negative affect 3, it's a little bit higher. But for the most part, this is going to be where model misfit comes into play. The degree to which these correlations bounce around from a overall average correlation that's based on the amount of unreliability that it gets extracted. So the implied correlation will go up because we're going to get rid of the unreliable variance here and unreliable variance here. So with an exploratory factor analysis, you get the loadings of all items on each construct. So here I've taken a two-factor solution. The first factor is clearly positive affect, and the second factor is negative affect. And this is the factor loading matrix. So and this is also after rotation. So what you see here is these numbers average 0, but they're not exactly 0. And these numbers average 0, but each one is not exactly 0. And then you get the best possible loadings for these two constructs. But in exploratory factor analysis, you have to do what's called factor rotation to determine the strength of the correlation between the positive affect factor and the negative affect factor. Well, when we go to a confirmatory factor analysis model, we are going to specify the rotated factor solution with the idea that these numbers right here, the 0.06 and negative 0.04 and negative 0.02, are essentially 0. Therefore, I'm going to fix them to be 0. And over here, this 0.13 and negative 0.09 and negative 0.04 are essentially 0. So we're going to fix them to 0. Well, that gives us 6 degrees of freedom back for not estimating these particular loadings. And what that allows us to do is actually estimate now the correlation between these two factors rather than doing it as a post-estimation rotation. When you do an exploratory factor analysis, you don't estimate the correlation. It's a post-estimation rotation process that determines the degree to which the two factors are correlated. So if you had questions about, Well, is the strength of that correlation stronger in males than in females? There's no way to test that. But when we go to confirmatory factor analysis, we can. So if I was going to, here the rotated factor correlation comes out to be -28. If I was to draw the diagram of what that would look like, this might be one way of representing it. But again, this -28 is not a parameter estimate of the model. It's something that we derive after rotation to show the strength of the association. And I haven't put the residuals in here just because this drawing would get a little bit messy otherwise. But again, when we convert to a confirmatory factor analysis model, we're going to take these three parameters and fix them to be 0. And we're going to take these three parameters and fix them to be 0. In the exploratory factor analysis model, we have a saturated model. We have, there's no model fit information. But when we go to the CFA and we fix these to be 0 and we fix these to be 0, now we're going to have model misfit that we can evaluate. Have we lost too much misfit? Are any of these parameters actually needed or necessary to be included as part of my overall model to achieve a satisfactory level of model fit? The other thing to note here is that I'm using the fixed factor method of identification. That's how exploratory factor analysis identifies its solution. It fixes the factor variance at 1. Right, so we remove the trivial loadings. And now we recast the drawing typically to look more like this. So we have positive affect with its 3 indicators underneath it, and then we have negative affect with its indicators underneath it. I've labeled each of the parameters that are possible, and notice here I'm going to use the fixed factor method of scaling. So I'm fixing the factor loading at 1. That makes positive affect just identified. I have 1, 2, 3, 4, 5, 6 parameter estimates, and I have the 3 variances and the 3 covariances. So positive affect is just identified. Negative affect is just identified. But the model itself is over-identified. This model actually has 8 degrees of freedom. Let's go back to the correlation matrix real quick. There it is. Because you'll notice, okay, with this part being just identified, there are no degrees of freedom that come from here. And with this part being just identified, there's no degrees of freedom that come from here. But you'll notice that there are 9 possible correlations between the indicators of positive affect and the indicators of negative affect. We're going to make one additional parameter estimate, and that is the correlation between the latent construct of positive affect and the latent construct of negative affect. So we're going to use 1 degree of freedom from these 9 observed correlations, and that means that the model will have 8 degrees of freedom when we estimate it. Now here is, back. So here's the model. And we've labeled each parameter. So if we did the tracing rules, we can start with our finger on great. We can go up lambda 1, 1, around psi 1, 1, back down lambda 1, 1. So it's lambda 1, 1 squared plus theta gives me the total variance of great. Lambda 1, 1 times 1 times lambda 2, 1 gives me the covariance between lambda 1, 1 or between great and cheerful. Lambda 1, 1 times psi 2, 1 times lambda 4, 2 gives me the correlation between great and sad. And if I went up, over, down, up, over, down, up, over, down, up, over, down, all possible times, I get this matrix. So this is the model implied covariance correlation matrix. The first cell, lambda 1, 1 times psi 1, 1 times lambda 1, 1 plus theta 1, 1 is the variance of great. Lambda 1, 1 times psi 1, 1 times lambda 2, 1 is the correlation between great and cheerful. And if I go, let's say lambda 1, 1 times psi 2, 1 times lambda 5, 2 is the correlation between great and down. Now this formula up here, sigma, is the Greek letter that we use to designate the model implied covariance matrix that is being reproduced through the matrix algebra listed in the slide. And we get there by taking the lambda matrix, multiplying it times the psi matrix, and then post-multiplying it by the transpose of the original lambda matrix, so we can get the lambda 1 squared, or the lambda 2 times lambda 3 and then we add the theta matrix to the resulting after the multiplication of this is done. And the theta matrix is a symmetric diagonal matrix. It only has variance estimates on that diagonal, and it has zeros everywhere else. So it's not adding anything else into the cells when we don't have any correlated residuals being estimated. Now, for those of you who like Greek and are geeks about math, this is what the lambda matrix would look like. It would have the 3 loadings on positive affect. It would have the 3 loadings for the negative items on the negative affect construct. So it's a 6x2 matrix. The psi matrix has variances on the diagonal and correlations off the diagonal. So psi 2,1 and psi 1,2 are essentially the same thing. It's a symmetric matrix. When you transpose a matrix, you just grab it by the corner and flip it. So now the lambda 1, 1, 2, 1, 3, 1 are here. It's a 2x6 matrix. So I just flipped it. And then here's the diagonal residual matrix. When I multiply a 6x2 and a 2x2, I get a 6x2 matrix. All right, so now you see that I brought in psi 1,1 and psi 1,2, as well as psi 2,1 and psi 2,2 into the matrix. Then when I multiply it times the transpose, now I make the matrix a 6x6 symmetric matrix. So everything above the diagonal, is exactly the same as what's below the diagonal. And then I add the theta matrix into the equation, and all it does is puts the unexplained variance onto each of the diagonal elements. And so essentially what's happening behind the scenes is the SEM software is using covariance algebra just like this to optimize what the parameters of this matrix should be to get as close as possible to look like the observed correlations that went into are being fed into the SEM software. There are different estimation processes to get those parameter estimates. We generally rely primarily on maximum likelihood. There's what's called robust maximum likelihood, which attempts to adjust the standard errors when you have non-normal data. I don't recommend that. ML works better and you lose the ability to make nested model comparisons. You can use generalized least squares, weighted least squares. The weighted least squares is pretty common when you have categorical indicators, but we usually can avoid categorical indicator. Oh, I'm sorry, didn't mean to do that. Which way? Okay. We can avoid categorical indicators by parceling items so that they become sufficiently metrical that we can go back to maximum likelihood. And then there's also bootstrap estimation and Bayesian estimation, which are typically options either within the software or like with Lavon, there's a software package called Blavon that does the Bayesian version of Lavon. So again, focusing on maximum likelihood. This just kind of describes what the others can do. Preferred is ML. It requires larger sample sizes and it requires multivariate normality be satisfied, but it's also very robust to violations of the assumptions, including the multivariate normal. So it's trying to identify the parameter estimates that are most likely to give rise to the observed data. And the likelihood is conceptually similar to a probability, but it's an iterative procedure that is basically trying to maximize the log of the likelihood function. Right? And so it's an iterative process. It starts with some best guesses, typically using 2-stage least squares. And then it goes from there to say, well, let me tweak this parameter by a little bit going this direction and this parameter by a little bit going this direction. Do I get closer to the observed matrix? And it goes back and forth that way until it says, okay, these are all the parameter estimates that are as close as I can get them to be what they need to be. in order to give rise to the observed data. Okay, I just said that. Okay. Now, the log L surface when estimating multiple parameters, it can be, this is an example of what a maximum likelihood terrain might look like. And the reason I'm pointing this out is that the idea is that it climbs to the top of the hill. You start with a bunch of points on this stuff here, and through the iterative process, it wants to climb and get to the peak of a roof or of the hill. And once it hits the peak of that hill, then the parameter estimates that are in the model are the most likely to give rise to the data. But you can see if I started down here and decided to start climbing over this hill, well, there's another hill that gets pretty darn close to this other one, but it's not the same. So we call this a local maxima, meaning we've gotten stuck at the top of a high peak, but it's not the correct high peak. And sometimes you can get this like M+, you can ask it to do multiple starts. So it chooses the pathway that looks like the most likely to lead to the correct top. And you can also sometimes identify local maxima when you have standard errors in part of your model that are noticeably larger than standard errors in other parts of your model. The other thing you can do to avoid local maxima is to provide start values. And rather than just letting it be a random start somewhere down in the bottom of the hill, you might say, hey, I know what this is the hill that we're climbing to because I've seen the observed correlations. So I know what the loading should about be. I know what the correlation should about be. So you can go ahead and put those expectations into the SEM software as start values, and then it'll just zip, go right to the top of the hill, the correct hill. All right, so the fit function is basically taking the fitted covariance matrix and then getting the trace of the observed matrix and the transpose of the fitted matrix to see how much deviations are we getting from that. You subtract out the log of the S matrix and subtract the number of parameters, and then you just iteratively keep changing the numbers in sigma until this is as small as it gets as small as it can get, and the change from one iteration to the next is essentially negligible. We get the actual chi-square value by multiplying sample size -1 and multiplying that times the fit function. Okay, so finding an optimal model and evaluating models, we're going to introduce the model fit indices as well as model modifications, and to find the best fitting and most theoretically sound SEM model. Again, here's the constructs with the parameter labels. You notice now that I've moved away from the Greek and I'm using LY for lambda, and I'm using TE for theta, and I'm using PS for psi. That's just because that's what Lisserl calls them. And so with what I like about the Lisserl models, we're actually fitting the true Lisserl model. M+, when you use the on and by commands, those commands basically generate the Lisserl model. So when you ask for the technical output, you will see a matrix called lambda that will have the first three columns of the first three rows of the first column with estimates, and the next three rows of the second column with estimates. So you will see those matrices that I showed earlier, the matrix algebra. The Lisserl model is in fact a direct rendering of the list of the matrix algebra, whereas Lavon and M+ use a different front end, but then convert your front end into the Lisserl model. So now here is the CFA fitting those the great, cheerful, and happy and sad. You'll notice we have one correlation representing positive affects, so that the 9 possible correlations of great, cheerful, happy with sad, down, and unhappy are all going up through this -31 and then down through one of the loadings. So we've used up 1 degree of freedom from those 9 possible correlations. So this model has 8 degrees of freedom. And the chi-square, based on a sample size of 759, turns out to be 50.56. The RMSEA is at the 0.08 level, which is the level of acceptable, especially when the confidence interval is definitely within 0.08. Our comparative fit index, CFI, we like to see this number to be above 0.90. And when we're above 0.95, we have outstanding fit. And the same for the Tucker-Lewis index, sometimes called the non-norm fit index, that has a value of 0.96. Like the CFI, we want to see that to be above 0.9, and above 0.95, we get into that outstanding level of fit. 9.0 is acceptable. 9.5 is outstanding. So we're acceptable, outstanding, outstanding. So overall, we would declare this model a well-fitting model. But that doesn't mean we stop and not examine for any kind of local misfit. But here, let's take a look at the model implied matrix. This is sometimes called the fitted covariance matrix. And the big thing to note is now the correlations, the model implied correlations in this part of the model are much more uniform than the observed correlations. So the model misfit is all due to the deviations of these observed correlations from these model implied correlations. With our heuristics for evaluating model fit, we would say that these deviations from this more homogeneous set is pretty trivial. We also get what's called the fitted residuals, which is the observed correlations minus the model implied correlations. And what you see is where we have a just identified situation, we've got almost no misfit within each construct. Our misfit, our fitted residuals are primarily going to be between the constructs. They should average 0, right? And generally we like that we like them to be normally distributed. Now, many software packages don't give you that information, which is unfortunate. Lisserl does, which is one of the reasons why I still like playing around with Lisserl, because if you have an outlier among your fitted residuals, that's an indication that something is wrong. Now, usually that indication shows up in model modification indices, which all software packages will give you. So the chi-square, it's calculated as n-1 times the minimum of the fit function, but it's conceptually similar to an ordinary chi-square. The value observed minus the value expected divided by the value expected, all right? And so if we look at the sample, model implied, that's conceptually for each cell, how we would calculate the chi-square. Now, the thing about the chi-square is it will rarely be non-significant. Now, in Zach's generated example, it was. In real-world data, it's usually not, particularly because we have it's sensitive to both degrees of freedom and sample size. So even though we've got a small model with not very many degrees of freedom, we have a large sample size. So the chi-square was significant for our simple example here. Now, model modification indices are basically telling you how much will the chi-square go down if the indicated parameter is allowed to be estimated. So we estimated great, cheerful, happy as loadings on positive affect, and we estimated sad, down, and unhappy on negative affect, but we didn't estimate positive affect items onto the negative affect construct, nor did we do the negative affect items onto the positive affect items or construct. And in addition, we didn't allow any correlated residuals. All right, so we're assuming that all of the residuals, the relationships among the residual variances are all 0 in the population. And this matrix tells us, well, wait a minute, there might be some correlated residuals, like great and sad would lead to a reduction in the chi-square of 16.52. If I allowed SAD to cross load on positive affect, I would get a reduction of 27.9. Or I could fix the issue by allowing down and unhappy to correlate with each other. Now, theoretically, there's no good reason for why SAD could cross load on positive affect. It's quite likely that this is just a sampling perturbation, and it's not real in the population. There's no theory that could support why SAD would want to go and cross load with the positive affect construct. But okay, here's the same model modification indices with M+ output. This was from the Lisserl output. And I believe that Levon will look a lot like this. It'll have by statements with their model modifications and then with statements with their model modifications. Right, so these are cross loadings, the by statement, and these are correlated residuals.
Dr. Little, could you repeat
Yes.
that again? We're allowing SAD to correlate. We're fixing a correlation with what?
Right now, SAD does not have it doesn't have a cross loading. It only
Okay.
loads on its negative affect. Right. This is after we estimated this model.
Right. We're
right?
trying to see if we can.
So, is there anything that would improve the model fit? Although we're
Okay.
already at an acceptable level, right? Actually, an outstanding level. We're just going to try to evaluate, are there places that could improve model fit? So
Okay.
we had a correlated residual between down and unhappy. And we also had the suggestion for cross-loading from SAD over to positive affect. And then there was a suggestion for a correlated residual from SAD to great.
Okay, so you're testing each at a time.
Yeah, but part of this is going to be consideration of, is there a model modification index that's large enough for us to even worry about? And two, does it make theoretical sense?
Okay,
Now, I work with these positive affect items all the time, and they don't have cross-loading, they don't have correlated residuals, right? So there's no theoretical reason for it. So for this particular application and this particular sample, this is just sampling error that's giving us these perturbations in here.
okay,
But we still get reasonably large modification indices. And one of the things to notice is this 27.90 and this 27.90 are indicative of the same residual misfit problem. So one way I can fix it is to allow a correlated residual. The other way I can fix it is to allow a cross-loading. Right? And then there's a different issue in here, smaller, where great and SAD want to correlate with each other. Now, we get the same model modification indices out of M+. One of the things you can do in M+ is you can say, well, just show me modification indices that are greater than 10. What Lisserl does is it likes to give you every model modification in its matrix formulation. So what would happen if we decided to allow SAD to cross-load on positive affect? If we used M+ syntax, we would just simply add SAD into our by statement. So we're putting the asterisk here to freely estimate great. I use the asterisk as a fixed parameter in my slides. My slides outdate M+, so I'm not going to go back in and change to be M+.
nope,
Yeah. But so just remember that the asterisk in M+ is to free that parameter. My asterisks in my diagrams is to show you which ones have been fixed. In Lisserl, the notation would be to free lambda y4 one, which is the fourth item onto the first construct. Let's go back here. Okay, so that does change the matrix algebra formulation. Now what's going to happen is I'm going to have psi 2,1 and lambda 4,2 worked into each of the cells for these three positive affect indicators. And then also the variance of SAD is now going to be a weird amalgamation of the loading squared on the negative affect items plus the loading squared on the positive affect construct, plus 2 times the SAD loading on positive affect times the SAD loading on negative affect times the correlation between the two plus the residual. So it makes the covariance algebra a little bit more complex, but we don't have to hand calculate this, right? We'll let the computer do this. Right? And in so doing, we get a loading of 0.18 for SAD on positive affect. It's only about 3% of additional variance being explained in SAD. Yes, we did get improvement in model fit, but it's theoretically does not make sense. So the red parameters are the ones that changed slightly from when we said SAD should not have a cross loading to this model where we said, okay, SAD, you can have a cross loading. But because it doesn't make theoretical sense, we're going to go back and say, no, it doesn't help the model in anything appreciably, and it makes no theoretical sense. I think that's just sampling variability. Now, if I was tempted again to go, okay, here's the revised residuals. You can see that we smooth things out again. So let's say I tried to fix it by allowing the correlated residual of 6 and 5 to go together. Now remember, this is just identified. We have 6 covariances and 6 variances, and the 6 parameters that we need to make are the 3 loadings and the 3 residual variances. If I try to throw another parameter estimate in here, it's not going to be identified, and you will get an out of bounds solution. But here again is what we're saying is that we're just going to add lambda 6.5 into that one cell to fix covariance estimate between down and unhappy. And here you see what happens when we get, yes, we got the same improvement in model fit, but now our parameter estimates are out of bounds. We have a negative residual, which is large. Now you shouldn't have negative residuals, but in SEM, it's important to note that you can get negative residuals sometimes. And if they are small, like negative 0.03, you can just leave it be. It's still within the boundary of the SEM or of the maximum likelihood plane that we're basing all of our inferences on. If you fix it to be 0, you push that information into all the other parameter estimates, introducing bias. If it's large, then you probably have a model misspecification like this one. So this is not identified. We have very large negative residuals. It's not identified. It's a model misspecification. It cannot be done. Now I can go with a correlated residual between SAD and great, as that's identified. It's a correlated residual between the 2 constructs. And all it's doing is adding the residual information into the one cell where great and SAD collide, right? And here we can see that the residual covariance is 0.19. But again, there's no theoretical reason to understand why would the stuff that's in great, that's not related to positive affect, so the specific variance of great, why would it correlate with the specific variance of SAD after controlling for their respective late true score information? So this is the specific variance that wants to correlate, and there is no good reason that the specific variance of SAD would correlate with great, other than that this is just sampling variability. I'm going to stop my share unless you want me to go back to a slide. But that's a simple CFA and a brief introduction to model fit information, and looking at model modifications. And again, that's, I think, the biggest thing. At what point would you go back to your data and throw out an outlier? I would have already done outlier detections when I screen my data. And so sampling variability is not necessarily an outlier. It's enough consistency It's still within the realm of, you know, when you sample from a population, you will get variability above and beyond the expected parameter in the population. And that can be expected. And so one of the hardest things, or the most important things to do in SEM is to make that distinction. Is it true in the population? And usually what I do is, if you look at my screen, there's a very good visual when you're looking at a model modification index and you're scratching your temple, trying to figure out why would that happen. It's probably a sampling error. On the other hand, if you hit your forehead with the palm of your hand, it's like, oh, duh, I should have thought of that in the first place. Then it's probably real. It's easy to justify. The other thing, consult with your colleagues. If you've got a colleague that knows a little bit about SEM, ask him or her, what do you think? Is there anything you can see that why these two might go together? Right? You know, you could even email a good colleague that you might know these kinds of data. Say, do you have any reason why that might happen? No, I can't think of a good theoretical reason for it. All right, then I'm going to call it sampling error. So we're a little bit ahead of schedule. We got about 45 minutes. I'm thinking we could probably start with parcels. Is that the next lecture?
I do believe.
Okay.
Quick question on CFA. Could I have a paper that's in revise? But really all the paper is doing is taking a scale for listening and transposing it into a scale for speaking to see if it's truly communication. So a CFA would be the only analysis necessary because that's all I need.
Right. In that case,
Right.
I kind of, you might do a multiple group CFA to see if it holds for both males and females.
Hmm.
And we'll have an example of how to do multiple group CFA
Okay.
tomorrow.
Okay. But essentially to start, that would, if that didn't work, I mean, I've done it with regression, but I think I could do better. That's one reason, very simple way to start. Okay. So
Yeah.
this would really be the two different constructs. It'd be interesting, I guess, to look at it from that perspective, if they are
Yeah.
truly separate.
So you measured both listening and
I took the same scale and just flipped listening to speaking.
and did you get both of them to the same sample?
Yeah, same
Okay.
sample.
So what I can envision there is actually fitting both constructs, the listening and the speaking, and
Right.
testing the items for factorial invariance across listening and speaking in a CFA framework. And we're going to talk about that tomorrow. So
Okay.
when we get to that, let's bring your example back up so we can talk
Okay.
about how you would do that.
Okay. I'm going to share my screen. And we'll start talking about parcels. So parcels are a great way to measure your latent construct with a number of indicators. And then once you have 6, 9, however many number of indicators you have for a construct, to then average some of them together to get down to 3 indicators of a construct. And by doing this, we gain several benefits, but we also need to be mindful of the process we use to select which ones we average together. So in this lecture, we'll talk about what parceling is, the benefits to parceling, and some of the things you need to keep in mind when creating your parcels. And we'll also look at parceling in a multidimensional framework. So parceling comes from parcels, where you package things together. And it is the averaging or summing, but usually averaging, of two or more items to create a more reliable indicator of a construct. So in the manifest world, when you have a scale of items, a common practice is averaging them all together to create a scale score. We're not averaging all of them together. We're averaging them together to create basically three parcels, three indicators of a latent construct instead of just having one average score. So what you'll do is you'll create these parcels and then use these new parcels as indicators of a latent construct. That's why it's called a data pre-processing strategy. So here we have our example of positive and negative affect with 6 indicators each: great, cheerful, happy, good, glad, super, sad, down, unhappy, blue, bad, terrible. And we have our loadings, which all look relatively high. We have good model fit, CFI, TLI, pretty high. RMSCA is below that 0.08 threshold. So you already have a good fitting model. And here is the actual scale that was used. So we have a root. In the last 2 weeks, I have felt. And then we have great, cheerful, happy, good, glad, super, sad, down, unhappy, blue, bad, terrible. And these are measured on a, I believe, a Likert scale. And here are the modification indices for these items. So here's how strongly the positive worded items want to load on negative affect, and how strong the negative affect items want to load on the positive. Some of these are a little high, but nothing's really standing out. So we don't have any reason to add a dual factor loading. Also, theoretically, it doesn't make sense. And here we have the residual correlations. So we see a little one with glad and great, sad and great, cheerful and super, and then super and glad. So if we have some parameter estimates that may want to add a residual correlation, but we can't think of a reason to, one solution of these would be to parcel items together. So if I parcel glad and great, cheerful and good, happy and super, any residual covariance among these two now get isolated as their residual. So instead of having to add another parameter that may not be theoretically justifiable, by averaging these together, it just becomes part of my residual. It's no longer causing misfit in my model. So now when I fit my model to these new parceled indicators, I have higher factor loading, so higher communality. My residuals are lower. And my model fit, even though it was good before, it's still improved. Now looking at modification indices, we don't see anything else that stands out. So what we've done in this example, we have 9 indicators, is we average, in this case, items 1, 2, and 3 to make a parcel 1, average 4, 5, and 6 to make parcel 2, average 7, 8, and 9 to make parcel 3. So now I have 3 indicators of this construct made up of average scores among these manifest items. So we do want to acknowledge that there has been a controversy when it comes to parceling. There is a empiricist or conservative view that says parceling is akin to cheating because model data should be as close to the response of the individual as possible in order to avoid the potential imposition or arbitrary manufacturing of a false structure. They use terms like mask, conceal, camouflage, hide, disguise, cover up. Not really statistical terms. But then there's the pragmatic view that given that measurement is a strict rule-bound system that is defined, followed, and reported by the investigator, the level of aggregation used to represent the structure, the measurement process is a matter of choice and justification on part of the investigator. So when we do create parcels and we report our results, we report using parcels and the structure, the method we use to create them, and like what items went into which parcels. We're very transparent about the process. And use terms like removed unwanted, clean, reduce, minimize, or strengthen, talking about the relationships among the items and the variance in those items. And there's also the pseudo-Hobbesian view. Parcels should be avoided because researchers are ignorant or perhaps stupid and prone to make mistakes. And because of the unthoughtful or unaware application of parcels by unwitting researchers can lead to bias, they should be avoided. Now, this won't apply to us because we are not stupid, unwitting researchers, and we are taking time to learn how to construct parcels thoughtfully. I can be philosophical too. I think, therefore I eat. So here are the psychometric benefits of parceling. We have a higher reliability from the parcels compared to the manifest items, higher communality, and the ratio of common to unique factor variance is stronger. So, hello, Prince. Sorry, my desk just happens to be in the middle of the cat highway, so they'll occasionally make an appearance. You have a lower likelihood of distributional violations. So if you have one item that's skewed one way and another item that's skewed another, by averaging together, you return a more normal distributed item. And it also allows for smaller, more equal intervals between your scales. So for example, if you have a 4-point Likert scale, we have 1, 2, 3, and 4 as your numbers. By parceling them together, you get a more continuous representation of that parceled indicator. So you now have 1, 1.5, 2, 2.5. It gets us closer to that assumed continuous distribution. For modeling with parcels, it's beneficial when we have fewer parameters to estimate, especially if you're building larger models or longitudinal models. The number of items for each scale, for each construct, number of constructs at each time point, your model parameters can quickly become very large. So being able to parcel down and just have 3 indicators per construct kind of helps keep that model at a manageable size for the estimator. It also helps if you have a smaller sample size to have fewer parameters that you need to estimate. As a lower indicator to subject ratio. Over here. Okay. It also reduces sources of parsimony error. So if you have items that may have sources of sampling error. By parsing those together, you isolate that source of error. And again, it makes larger models more tractable and estimatable, especially if you're doing longitudinal modeling or modeling a lot of relationships among constructs. So here's kind of a diagram that represents all of the sources of variance that can be in our model. So we have 3 sources of true score variance. Each have their own unique source of variance. And we also have potential covariance among our constructs. And then each indicator has specific variance and error variance, but there may also be a residual covariance. So that's what this X is done here. And now a paper went through and did the matrix algebra to demonstrate that when, say, you parcel these 3 items together, the true score doesn't get reduced. The other sources of variance are a 1/9 of their original size. So we have a higher proportion of true score to error variance with the parcel compared to the manifest indicator. And in the case where we have this residual error variance down here, or this residual correlation, this S sub X, we see that it is 1/4 of its original size, and all the other sources of variance are 1/9 their original size, and it's contained in the residual, so it's no longer affecting model fit. And then we have this, if we have a item loading with a cross loading, that cross correlation that's shared among the constructs is 16/9 its original size, and everything else is a 1/9 original size. And then we have an uncorrelated construct with a cross loading. We see that the T1s are unaffected, but everything else is reduced. So here we have a depiction of sampling effects versus population effects. These thetas down here are residual correlations that are part of the population, while the dotted lines are part of the sample. But it's hard to tell unless you know specific sources of variance in here, what residual correlation is part of the population or part of the sample. So one thing we could do is average A1 and A3. So this residual covariance just becomes part of the residual. If we average A1 and B1, this cross-loading should go away, and this residual becomes part of the residual. This residual covariance becomes part of the residual variance. So what we're just trying to do is isolate these unmodeled parts of the variance covariance matrix, so we're not having misfit in our data. Now, there are some empirical cons. If parceling is done improperly and you have multidimensional constructs, it can be hard to interpret what that construct is now, because the construct is made of what is measuring it. So if you've averaged items together that are multidimensional, your construct then becomes multidimensional. And we'll talk about that when we talk about multidimensional parceling in a bit. another benefit of parceling is you have improved model fit, but just because you have improved model fit does not mean you've parceled correctly. So we want to be thoughtful when we construct our parcels. And if your research question is about the items themselves, you want to keep your analysis at the item level. And talking about parcel allocation variability, if you're parceling at random, which we don't recommend, then the amount of variability in, this paper just talking about parceling at random, they basically parceled every combination of items together and saw the variability in model fit across all possible combinations of items. And the more variable that is, the bigger impact the allocation has on model fit. So you want to only use random assignment of parcels if all your items are essentially interchangeable, which is rarely the case, which is why we don't really recommend random assignment. So parcels rely on two psychometric principles. Principle of aggregation, where any one item is less representative than an average of many items. And aggregating these items yields a greater precision on the underlying thing they're measuring. And the law of large numbers, where more is better, yielding more precise estimates of parameters, has a normalizing tendency. So here is our familiar construct centroid and our universe of items we can select for measuring this construct. Just taking laps today. Now I've selected 3 pairs of items, so 6 items in total. What we do by parceling is we take the mean, which places our parcel at the geometric center between the 2 points. So now these larger dots become our indicators, our parceled indicators of our construct. And they triangulate around that construct centroid. Here's another visual representation from Todd's book, where we have these items and the parcels in the middle triangulate around that construct. And parcels, as you average them together, move up selection planes. I know Todd talked about his selection plane diagram previously, but if your item level would be more down here, as you average together, you move up quite tighter and closer around that construct centroid. So we have 6 different items that we're going to parcel together. These are not close to each other. So the space in between them covers more space. It's a little bit around our construct centroid. Now in this example, we have items that are at the item level, not reliable indicators of our construct. This maybe has a cross-loading with a construct over here. This one maybe has a cross-loading with something over here. But even if we have unreliable indicators, we can make parcels of those. And those parcels now accurately capture our construct of interest. So we can start out with psychometrically poor items and get psychometrically useful parcels.
This is Kendra again. So why would you do that? A theoretical reason? I mean, if they're already not, like the red, psychometrically not. kind of outside your contract zone.
Well, they may
Construct.
capture part of this construct that these
Okay.
other items don't. So it may capture a dimension that is either hard to capture or is really correlated with something else.
Okay, highly correlate. Okay, I get, thank you.
So instead of removing those items, we're able to use parcels to use that information to.
So might that item cross-load somewhere else?
At the item level, it might. This one may have a positive loading over here. This one may have a negative loading over here.
Okay,
But if the parcel won't have any cross loadings.
right, great. Okay, thank you.
So what we're basically doing is we have our true score component, our specific component, and our error variance. And this goes back to that classical test theory little equation that I showed earlier this morning. So since our specific variance is assumed to be uncorrelated, it reduces. Error variance is uncorrelated, so it reduces. The construct variance is correlated, so it compounds. So we have a higher proportion of true score to error variance. Now, there's several ways to build parcels. One of which is know thy S. So we're basing our parcels on theory. And this version doesn't have the example of receive social support. But if I have 3 items that ask about family, 3 items that ask about friends, and 3 items that ask about significant others, and the perceived social support I have from them, all of those family, friends, and significant others are sources of specific variance. I can parcel those 3 items together and have a family parcel, a friend parcel, and a significant items or significant others parcel. So that what before would have had residual correlations now has just residual variance. So I'm able to look at items that have a residual variance and see what may these have in common other than what I'm trying to measure is a good way of identifying that source of specific variance and what items may be helpful to parcel together. Another way is random assignment, which again, we don't recommend unless you have a large number of indicators. A lot of this comes from like biological samples or fMRI readings, where they're essentially tau equivalent and interchangeable. So any random parcel allocation doesn't result in a significantly different or significantly better fitting model than any other random assortment. But in our kind of field, that's rare to occur. So the other technique is creating a balance of items. So the balancing technique requires looking at your item loadings and finding the items with the highest loading and averaging it with the item with the lowest loading. Second highest with second lowest, third highest with third lowest. This creates a set of balanced parcels. So what I tend to do is I will look at my modification indices for any sign of residual covariance due to like specific sources of variance. So I'll see if I have any cross-loadings or any residual correlations. And I'll make parcels based on those first. And after I've accounted for all of those, I will then make parcels based off of balance. That makes sense? Another way is to use a priori parseling schemes. It's not really common to have an established parceling scheme for a measure. The CAMI here is one example. But if you're developing a scale, you can also report in your norming sample what items went well when creating parcels, so that researchers who are using that scale in the future will have kind of a guideline with what worked in your norming sample. Are there any questions before I get to the multidimensional parcels?
Zach, how frequent, I guess it depends on your data, what you're doing. How, in your experience, is this common?
Yes. So typically every time I have a model to build, I have more than 3 indicators. So I will typically fit an item level CFA with however many indicators are for my construct. And then I will create parcels for those constructs based
Mhm.
on modification indices and item loadings. And then so I'll have in my result section, I'll have item level analysis and then parcel level analysis. And then I'll use that parcel model moving forward with the rest of my analyses.
And like you said, this may be consistent with other research that found the same parcels.
Right. So you want to verify that that parceling scheme works in your data.
Okay.
Because you may have an aspect of your sample may be different than a previously published study,
Right.
or you just may have sampling variability that got some residual error variance that wasn't shown in others. So you basically verify the parcel structure in your data.
Makes sense. So, you mean, again, you want to, don't parcel less than 3, right? I mean, you want to keep it, this is typically when you have a lot of items, right? For a particular construct.
I'll parcel when I have 4 items.
Oh, sometimes, okay. So it depends. The indicator you said is in the modification indices. That's where you
Yes.
get the suggestion to parcel?
Yes.
Okay.
If I go back a ways here.
I'm sorry, thank you.
You're good. So if I have like these residual correlations that are a little higher than the other ones, this is a modification index. So there's something with glad and great that wants to correlate above positive affect. So instead of adding this residual correlation, I'll just parcel glad and great together.
Okay, thanks.
Mhm.
And
You'll
if
see
there'd
that
be,
here.
how do you know if there'd be 3 items? Per
If you
parcel?
have parcels don't have to have the same amount of items.
Okay.
So if you see, so I can have glad, great, good, cheerful by itself, and then happy and super.
Okay,
You can mix and match parcels with manifest variables. So you can keep your regular indicator if it's like just a really good indicator of that construct,
okay.
and then parcel your other items together. So they don't have to be evenly distributed. They don't have to be all parcels. It's just.
Thank you.
Mhm. Too far. Okay. So one of the ways that I actually mostly use parcels, aside from just reducing the number of items, is when I have multidimensional constructs. So in this example, I'm measuring intelligence with a spatial scale, a verbal scale, and a numerical scale. So since my intelligence has 3 dimensions to it. There are 2 ways we can approach parceling. Think of these dimensions as subscales as well. So in a domain representative approach, I will mix the content from various dimensions. I'll have a parcel that has 1 spatial item, 1 verbal item, and 1 numerical item. So each of those dimensions of intelligence is represented in each parcel. Another way to do it, and the way I'll typically do it, is facet representative parceling, where each parcel represents a dimension of the construct. So I'll have a spatial parcel that is all 3 indicators from the spatial subscale. And again, this is our recommended method if you have this sort of measure. So here's kind of a graphical representation of domain parceling. So I have spatial, verbal, and numeric ability, or intellect. So the blue is intellective ability, and then spatial, verbal, and numerical are my specific sources of intellective ability. And for domain representative parceling, I'll have 1 of each in each parcel. And since our factors are built of what's in common among our items, my latent factor will represent intellective ability, spatial ability, verbal ability, and numerical ability. So it's my latent construct is now a multidimensional construct. But the reason why we don't recommend this very often is because we don't know which facet is driving relationships among other constructs with this one. Which part of which dimension is doing the driving? So in facet representative parcels, I have a spatial parcel, a verbal parcel, and a numerical parcel. And again, our common factor is what's in common among the items. I now have an intellective ability that is disentangled from what is spatial, verbal, and I've already forgot it, numeric. This way we can just look at the intellective ability we're interested in and leave behind that specific source of variance. And this is a more realistic case of what we're looking at. There's a higher amount of commonality. The intellective ability is a larger driver here. And then what's specific is left down below. Now, another way to represent this is a higher order model, where we have spatial, verbal, and numeric ability. What's in common is pulled up. And then again, what's in common is pulled up. So I now have a higher order construct of intellective ability, and then lower order constructs that represent each facet of intellective ability without the intellective ability part. Now, these 2 things are mathematically equivalent. So this intellective ability is the same amount of variance as this intellective ability. This model is a lot easier to estimate than having a higher order model. Which is why when I have subscales, I'll create subscale parcels. Because what I'm interested in is this higher order structure, or this higher construct of intellective ability. So if in your data you have different subscales that will lead into a higher order structure, we'll typically advise you to make parcels of those subscales to have an implicit higher order structure, because mathematically they're equivalent.
Which one did you recommend? The implicit or the
Yes.
explicit?
Implicit using parceling.
Okay.
So a good way to see when it's best to use which of these types of parceling, either facet or domain, is if you only care about what the common variance has to say about y. So if this regression is the one that you're interested in, then facet representative parceling is equivalent because that same information is predicting y. If instead you're interested in what each construct contributes to y, this is not identified, but domain will tell you what all of these facets predict y, though it is all kind of put together in the same source of variance. So this is a combination of each of these facets, unique influence on y.
Best way to tell whether you need to use domain representative parceling or use facet representative parceling is to look at the correlation of your multidimensional parceling scheme, both domain and facet representative, and then look at the correlation of that construct with 2 or 3 other constructs. And if whichever the way of creating parcels gives you the largest correlation with the other constructs, that would be your preferred method. If it's a mixed bag, so sometimes facet is higher, sometimes domain is higher, then you're going to have to rely primarily on the theoretical relevance. Now, if you go back slides, Zach, where we do, okay, yeah, it was one of the colored slides where we have back, it'll be into the domain representative is the one I want to get a.
Okay.
Okay, let's no, let's go back to the facet representative. That was the one I wanted. Okay,
Here.
that one will work.
Okay.
So the idea here is if there is something in the specific variance that wants to relate to another construct, it would show up as a dual factor loading when you do facet representative parcels. So you can examine that information as well as build a domain representative parcel and see if the correlation of it is higher with another construct than the facet representative version. And if it is about the same and the modification indices are just like for one or of these lower order facets, then you can just allow a dual factor loading to represent that relationship, that there's something about verbal ability that's not intellective ability that still wants to relate to another construct.
I do also want to point out that we've had some recent publications. There is a chapter in small sample size solutions about constructing parcels and an elements booklet about parcel and structural equation modeling, as well as several other papers that go into the merits of parceling, parcel versus items, and any other questions?
Sometimes do you discover a higher order construct or like, I'm going to say, does it emerge from the analysis to say, wow, there's a higher order construct in here and I can parcel it? Or do you usually know going into it?
Yeah, you're usually going to know going into it
Okay.
that there's going to be a theoretical, I mean, you recognize already that it's multidimensional. Sometimes though, like when you do your item level CFA, you might notice a pocket of correlated residuals, which would be
Right.
indicating that you might have a facet there. So sometimes the exploratory EFA of the items or CFA of the items might give you a hint that, hey, there are a couple, 3 pockets of highly correlated things. Like if you did an item level CFA of the social support scale that Zach has used in examples, you would see that all of the ones that have the word family in them would have a correlated residual with each other. And all of the ones that have peers in them would have a correlated residual within them.
Okay.
Yeah,
Right.
here's
And
that.
that would, yeah, so that those would show up as correlated residuals. And then there'd be an indication, hey, I've got 3 facets in here.
So facets are part of a higher order construct? No.
Well, you can also think of subscales,
Oh, subscales. Okay, subscales of the higher order construct.
right?
Okay.
In this case, these are more like method factors because using the word special person is unique to those 4 items, but
Yeah.
it doesn't have any theoretical relevance for social support. It's just a way of capturing the degree to which you think you have social support from special persons, from family, and from friends. So you can see that so those would be they're facets, but they're more like method facets and not substantive subscales.
Yeah.
Whereas if you were looking at something like internalizing or externalizing, there are very specific subscales that go together to represent internalizing and specific subscales that go together to represent externalizing.
Yeah, no, interesting. Okay. So where I find interest, I said I'm trying to look at listening and speaking as a more holistic climate creator in organizations. So I'm not sure they have the same facets, I guess, is what I'm thinking. But I'm trying to test that, right?
Yeah.
Or
Well, you'll be able to find that when you start doing an item level CFA of the speaking
yeah,
and the item level CFA of the listening. We can examine the I'll have to walk you through tomorrow, maybe when we have our consulting time.
yeah,
You will equate the item loadings on the respective constructs across listening and hearing,
right.
and you will correlate the residuals of the like items. That the only thing that changed was the listening versus the speaking.
Right. Or
And
maybe
then-
there's another facet I'm not even thinking of. Right. I mean, there might be more than talking and listening. I don't know. Okay. That
Right
makes
now,
sense.
you've only operationalized the 2. And so
Right.
my guess is that there are going to be
Yeah.
2 constructs, but the items might have smaller pockets in them. But if they exist in the listening items, they should also exist in the
Yeah.
speaking items.
Right. That's yeah, interesting. Thank you.
Okay, we are at our 3 o'clock stopping hour. Thanks everybody for a terrific first day. We'll have three more. I really want to encourage you to start thinking about your own data and bring some questions for us. We'd be more than happy to provide consultations. That's another one of the benefits of StatsCamp that you get is a lot of essentially consultation time on top of the presentations.